Picture the scene. On one side, a Greek philosopher stands beneath a star-filled sky, pondering the nature of matter with nothing but observation and reason. On the other, a modern scientist in a lab, surrounded by complex machinery, testing a hypothesis about the very same fundamental particles. These two figures, separated by thousands of years, might seem worlds apart, yet they are connected by a single, unbroken thread of human curiosity. What if I told you that many of the revolutionary ideas we credit to modern science, from atomic theory to the heliocentric model of the solar system, were first proposed in the ancient world? It's a staggering thought. Try to imagine our world without these foundational concepts. No understanding of germs causing disease, no framework for planetary motion, no concept that everything is made of tiny, indivisible units. Our technological landscape would be unrecognizable, built on entirely different and perhaps much weaker footings. The truth is, the scientific revolution didn't just appear out of a vacuum. It was a renaissance, a rediscovery and validation of insights that brilliant minds had already articulated centuries, even millennia before. We often think of ancient thinkers as being preoccupied with myths and abstract philosophy, but the reality is so much more thrilling. These individuals were the original scientists, using the tools available to them, logic, mathematics, and meticulous observation of the natural world, to propose theories that were breathtakingly ahead of their time. Some of their ideas were so revolutionary, so seemingly fantastical, that they were dismissed as pure imagination, only to be confirmed by hard evidence hundreds of years later. This video is a journey back to those origins. We are about to dive deep into 30 of the most incredible ancient theories that, against all odds, laid the essential groundwork for the scientific disciplines we know today. From medicine to physics, astronomy to biology, we will uncover the startling prescience of thinkers who dared to question the world around them with nothing but their intellect as a guide. This exploration is more than just a history lesson. It's a testament to the enduring power of a single, well-reasoned idea. It's a story of human imagination persevering across centuries, waiting for technology to catch up to its brilliance. You're about to discover how a theory conceived in a library in Alexandria could one day influence an experiment at CERN, or how a medical postulate from ancient India prefigured our understanding of the immune system. We'll encounter ideas that were lost, forgotten, and then miraculously found again, changing the course of human knowledge. So, get comfortable and prepare to have your perspective on history and science permanently shifted. The journey from ancient speculation to modern confirmation is a fascinating one, and it all starts right here. Our journey begins not in a laboratory, but in the sun-drenched agora of ancient Greece, around 450 years before the Common Era, with a philosopher named Democritus. While his contemporaries were debating whether the universe was made of water or air or an unending cycle of fire, Democritus and his teacher Leucippus proposed a theory that was so radical, so utterly foreign, it must have seemed like science fiction. They called their fundamental building block of reality atomos, a Greek word meaning uncuttable or indivisible. Just let that sink in for a moment. Over 2 millennia before we could ever hope to see such a thing, these thinkers conceived of a universe built from tiny, eternal, and unbreakable particles. They arrived at this stunning conclusion not through experiment, but through a powerful exercise in pure logic. Democritus reasoned that if you were to take a piece of cheese or a stone or even a drop of water and began cutting it in half and then in half again, you would eventually reach a point where it could no longer be divided. This final, fundamental speck was the atomos. He imagined these atoms as being infinite in number, perpetually in motion within a void, and differing from one another only in their shape, size, and perhaps their texture. The world we experience, with its solid earth, flowing rivers, and dissipating smoke, was simply a consequence of these different atoms colliding and hooking together in an infinite cosmic dance. The sharp, bitter taste of a lemon that was caused by atoms with jagged, rough shapes, the smooth flow of olive oil, those were perfectly round, slick atoms sliding past one another. Now contrast this with the prevailing wisdom of the time, which was largely based on the teachings of Aristotle. He championed the idea of four fundamental elements: earth, air, fire, and water. This was an intuitive system. You could feel the earth, breathe the air, see the fire, and drink the water. It made sense on a human scale, but Democritus was digging deeper, looking for a reality beyond human perception. His atomic theory was a direct challenge to this elemental view, suggesting that earth, air, fire, and water were not fundamental at all, but were themselves just temporary arrangements of much more basic, invisible particles. For centuries, the Aristotelian view won out. It was more comfortable, more aligned with everyday experience. The idea of a void, of empty space, was particularly troubling to philosophers who believed nature abhors a vacuum. So, the atomic theory was largely shelved, a fascinating but ultimately dismissed footnote in the history of philosophy. Yet, the idea refused to die completely. It was preserved in the texts of a few later thinkers, waiting. Then, in the early 19th century, an English schoolteacher named John Dalton, through his meticulous work with chemical gases, independently arrived at a very similar conclusion. He proposed that all elements are composed of atoms, and that chemical reactions are merely the rearrangement of these indestructible particles. The philosophical speculation of Democritus had found its experimental proof. The very foundation of modern chemistry, and later, the entire field of particle physics with its quarks and leptons, rests upon this ancient, brilliant, and startlingly accurate intuition. Democritus couldn't see the atom, but he absolutely saw its necessity. While Democritus was looking inward, imagining the infinitesimally small, another Greek mind was gazing outward and reconfiguring the entire cosmos. Just a century after the atomic theory was proposed, a man named Aristarchus of Samos dared to propose an idea so audacious it was almost universally rejected for nearly 2,000 years. He looked at the sky and declared that the Earth was not the immovable center of the universe. Instead, he placed the Sun at the center, with our planet and all the others spinning in orbits around it. This was the heliocentric model, a radical departure from everything his society believed, and it was conceived in the 3rd century before the Common Era. To understand just how revolutionary this was, you have to step into the mindset of the ancient world. The geocentric view, with a stationary Earth at the center of everything, wasn't just a scientific theory, it was a philosophical and almost theological cornerstone. It felt intuitively correct. We don't feel the ground moving beneath our feet. We see the sun, moon, and stars rise and set, appearing to circle us. This Earth-centered universe also placed humanity in a position of cosmic importance, a comforting thought that resonated with philosophical and religious doctrines of the time. Aristarchus was challenging not just a scientific consensus, but the very place of humanity in the cosmos. His proposal was met with deep resistance, most famously from the towering figure of Archimedes, who wrote about the Samian's theory almost with disbelief, treating it as an abstract mathematical curiosity rather than a physical reality. The cultural and philosophical weight of geocentrism was simply too heavy for a single voice to lift. But Aristarchus wasn't just a philosophical rebel. He was a brilliant mathematical astronomer, and his heliocentric idea was born from meticulous observation and calculation. In his only surviving work, On the Sizes and Distances of the Sun and Moon, he demonstrates a methodology that was centuries ahead of its time. He didn't have telescopes or advanced instruments, so he used geometry and the power of his own reason. He carefully observed the moon during a lunar eclipse, recognizing that the curved shadow of the Earth falling upon it could reveal their relative sizes. He then waited for the moment of a half-moon, understanding that at that precise instant the sun, earth, and moon would form a right triangle. By measuring the angle between the moon and the sun in the sky at that moment, he could use trigonometry to estimate their relative distances. While his actual measurements were inaccurate due to the limitations of his tools, he concluded the sun was about 20 times farther away than the moon. When it's actually closer to 400, the method itself was flawless, a genuine precursor to the entire field of astronomical measurement. He was proving that the heavens could be measured and understood through mathematics. The true tragedy of Aristarchus is not that he was wrong, but that he was so nearly lost to history. His original text outlining the heliocentric system has completely vanished, wiped from the record by the overwhelming tide of Aristotelian and later Ptolemaic geocentrism. We know of his revolutionary idea only because other writers, like Archimedes, mentioned it in passing, often to refute it. This loss is incalculable. Imagine if his work had been preserved, studied, and built upon. The entire trajectory of astronomy could have been accelerated by well over a millennium. Instead, his insight became a scientific dead end, a brilliant flicker of light that was snuffed out, forcing figures like Copernicus to essentially reinvent the wheel in the 16th century. Copernicus himself was aware of Aristarchus, acknowledging the ancient precedent in an early draft of his own work, though he later removed the reference. It's a haunting thought. The core idea that sparked the Copernican revolution was alive and well in the ancient world, waiting in forgotten scrolls for its moment to return. Now, let's shift our focus from the grand scale of the cosmos to the intricate inner workings of the human body. Around the same time that philosophers were contemplating atoms and planetary motions, a revolution of a different kind was taking place on the island of Kos, led by a figure we now call the father of medicine, Hippocrates. Before his time, illness was widely seen as a supernatural affair, a punishment from an angry god, the work of a malevolent spirit, or the result of a curse. The primary healers were priests, and treatments involved rituals, sacrifices, and prayers aimed at appeasing divine forces. Hippocrates and his followers ushered in a radical new paradigm. They proposed that disease was not a divine punishment, but a natural phenomenon with a physical cause that could be studied, understood, and treated through rational means. This was the birth of clinical medicine, and its central organizing principle was the theory of the four humors. This theory posited that our bodies contained four key fluids or humors: blood, phlegm, yellow bile, and black bile. Health was not a gift from the gods, but a state of perfect balance between these four substances. Conversely, illness was simply an imbalance, an excess or a deficiency of one or more humors. Each humor was linked to a specific season, a pair of fundamental qualities, and even a personality trait, creating a holistic view of the human condition. Blood, associated with the spring, was warm and moist, and its ideal balance gave a person a sanguine or cheerful and passionate temperament. Phlegm, connected to winter, was cold and moist, and in balance it led to a calm, unemotional phlegmatic disposition. Yellow bile, the humor of summer, was warm and dry, and its balance created a choleric personality, ambitious and easily angered. Finally, black bile, tied to autumn, was cold and dry, and its proper balance resulted in a melancholic, thoughtful, and often creative individual. This framework, while ultimately incorrect in its biological details, provided physicians with their first systematic tool for diagnosis and treatment. A doctor wouldn't simply blame a fever on a god's wrath. He would observe the patient. A flushed face and a rapid pulse indicated an excess of hot, moist blood. A treatment, therefore, might involve cooling and drying the body, perhaps through a diet of cool foods or the most famous remedy of all, bloodletting. The goal was always to restore the body's natural equilibrium. This emphasis on direct clinical observation was perhaps Hippocrates' greatest legacy. He taught his students to note everything: the patient's breathing, their sleep patterns, the color of their urine, the appearance of their tongue. This meticulous gathering of evidence is the very bedrock of modern medical diagnosis. The famous Hippocratic Oath, with its central tenet of "first, do no harm," emerged from this new, rational, and ethical approach to healing. The influence of this idea of balance is so profound that it echoes in our language and our wellness philosophies even today. We still describe someone as being in good humor or bilious. When we feel optimistic, we call it sanguine, a direct link to the blood humor. The concept that health is a state of internal equilibrium is a cornerstone of many alternative and holistic medicine practices. While we now know that diseases are caused by pathogens, genetic disorders, and environmental factors, the humoral theory's core intuition that the body is a complex system that strives for balance was a powerful and enduring one. It shifted the responsibility for health from the celestial to the terrestrial, from the altars of the gods to the hands of physicians. It established the principle that the human body operates according to understandable natural laws, and that by carefully observing those laws we can intervene to heal. This was the crucial first step on the long road to modern medicine. Moving from the vast inner workings of the human body to the very shape of our world, we encounter another staggering feat of ancient intellect that stands as a monument to the power of applied reason. At a time when many cultures still envisioned the Earth as a flat disk or a floating island, a handful of Greek thinkers had already deduced its spherical nature. Sailors observed that ships disappeared hull first over the horizon, and travelers noted that different constellations became visible as one moved north or south. But knowing the Earth was a sphere was one thing. Measuring its size was an entirely different challenge, one that seemed almost absurd in its ambition. That is, until Eratosthenes, the chief librarian of the Great Library of Alexandria, decided to measure the entire planet using little more than a stick, the sun, and a brilliant grasp of geometry. His ingenious experiment hinged on a simple yet profound observation. Eratosthenes had learned from travelers that in the southern city of Syene, now modern-day Aswan, something remarkable happened every year at noon on the summer solstice. The sun shone directly overhead, so perfectly vertical that its light reached the bottom of deep wells and objects cast no shadow whatsoever. This told him that in Syene, the sun was at the zenith. Meanwhile, in his home city of Alexandria, which lay almost directly north of Syene, vertical objects like a gnomon, a simple stick placed in the ground, did cast a shadow at that same moment. This meant the sun's rays were striking Alexandria at an angle. Eratosthenes realized that this difference in angle wasn't just a local curiosity, it was a direct measurement of the Earth's curvature. He was essentially using the sun as a giant measuring tool, with its parallel rays acting like a cosmic ruler, so he set to work with meticulous care. First, he measured the length of the shadow cast by a vertical stick in Alexandria at that precise solstice noon. Using basic geometry, he could then calculate the angle of the sun's rays. He determined this angle to be about 7.2 degrees, which is exactly 1/50th of a full 360-degree circle. Now came the second crucial piece of information, the distance between Alexandria and Syene. He hired bematists, professional surveyors trained to measure distances by pacing, to ascertain the overland route. They calculated the distance to be roughly 5,000 stadia. The logic that followed was breathtakingly elegant. Eratosthenes reasoned that if 7.2 degrees of the Earth's circumference corresponded to a distance of 5,000 stadia, then the full 360 degrees must be 50 times that distance. Simple multiplication gave him a total circumference of 250,000 stadia. The true test of any scientific claim is its accuracy, and here Eratosthenes' result is nothing short of astonishing. Converting ancient stadia to modern units is tricky, as there were different standards, but using the most likely Attic stadion, his calculation translates to about 25,000 miles. The actual polar circumference of the Earth is approximately 24,860 miles. This means that over 2,200 years ago, using a stick and his intellect, Eratosthenes measured the size of our planet to within an accuracy of about 1%. It was not a rough guess or a philosophical speculation. It was a rigorous, empirical, and calculated measurement that stands as one of the most brilliant experiments in the entire history of science. This single act of genius proved beyond any reasonable doubt that the Earth was not only round but was a sphere of a knowable, quantifiable size. The implications of this discovery ripple far beyond the dusty courtyards of Alexandria. By establishing the Earth's true dimensions, Eratosthenes gave future explorers a tangible scale for their ambitions. His work provided the foundational geographical knowledge that would, centuries later, inspire figures like Christopher Columbus. While the popular myth suggests Columbus was proving the Earth was round, the educated Europeans of his time already knew that. The real debate was over the size of the Asian landmass and the width of the Atlantic, a debate rooted in the data Eratosthenes had produced. More importantly, his methodology became a blueprint for all future scientific inquiry. He demonstrated how careful observation, coupled with logical deduction and mathematical principles, could unlock the deepest secrets of the natural world. He measured the Earth not by traveling around it, but by thinking about it, setting a precedent for empirical science that would inspire astronomers and geographers for millennia to come. But while Eratosthenes was measuring the world, another Greek thinker, working over 2 centuries earlier, was wrestling with an even more fundamental question: where did life itself come from? In the bustling city of Miletus, a philosopher named Anaximander gazed out at the sea and envisioned a story of origins that was, in its essence, a breathtaking precursor to the theory of evolution. At a time when the dominant creation myths involved gods fashioning humans from clay or summoning animals into being by divine command, Anaximander proposed a radical, naturalistic alternative. He suggested that all life, including human life, first emerged from a watery abyss, and that the first animals were born from a kind of primordial slime heated by the sun. Even more astonishingly, he argued that these initial life forms were not the complex creatures we see today, but were simpler, and that over vast stretches of time, they gradually transformed, with some species giving rise to others in a slow, continuous process of change. His reasoning for human evolution was particularly insightful and rooted in a simple, observable fact of nature: the profound helplessness of human infants. Anaximander observed that a newborn human requires an exceptionally long period of nurturing and care before it can survive on its own, unlike the young of many other animals which can walk or find food relatively quickly. He logically concluded that if the first humans had appeared in the world as fragile, helpless babies, they could never have survived. Therefore, he deduced, humans must have originated from another kind of creature, a creature that was already self-sufficient and required less parental investment. He famously speculated that this ancestor was a fish-like animal, proposing that humans were, in a sense, nurtured inside such a creature until they were mature enough to emerge and survive on land. This was a staggering leap of logic, one that replaced divine intervention with a natural, step-by-step process of development driven by necessity and survival. To truly appreciate the audacity of this idea, you have to consider the intellectual landscape of the 6th century before the Common Era. The prevailing worldview was one of stability and fixed kinds. The world and its inhabitants were generally seen as being created in their current, perfect forms. Anaximander was challenging this notion at its core, replacing a static creation with a dynamic, ongoing transformation. He didn't have the concept of natural selection or genetic mutation, but he had grasped the fundamental principle of evolution. that life is not static, that species change over time, and that all living things are connected through a long, branching lineage. He even touched upon the idea of extinction, suggesting that if a species failed to adapt to a changing world, it would simply perish. This was a cosmology in flux, a world where nothing was permanent and everything was subject to the slow, grinding wheels of time and environmental pressure. The parallels to Charles Darwin's work, published over 2 millennia later, are hauntingly clear. Both men looked at the biological world and saw a story of descent with modification. Both understood that the immense diversity of life could be explained by common ancestry and adaptation. Where Darwin had the fossil record and the observations from his voyage on the HMS Beagle, Anaximander had the power of pure reason and a fearless willingness to follow the evidence wherever it led, even if it led to conclusions that stripped humanity of its privileged, separately created status. He planted a seed of biological thought that would lie dormant for centuries, a radical suggestion that the history of life was written not in the stars, but in the very bodies of the creatures around us. His vision of life crawling from the water to inhabit the land is a narrative that modern paleontology has overwhelmingly confirmed, a testament to the incredible prescience of a mind that dared to think biologically in an age of myth. From the biological evolution envisioned by Anaximander, we now turn to a very different kind of order, an order not of flesh and transformation, but of pure number and eternal ratio. In southern Italy, around the 6th century before the Common Era, a mystical and philosophical school emerged under the guidance of Pythagoras, a man whose name is now synonymous with triangles, but whose actual vision was infinitely grander. The Pythagoreans didn't just see mathematics as a useful tool, they perceived it as the very substance of reality. They believed that the universe, at its deepest and most fundamental level, was not made of earth or fire, but of mathematics. For them, numbers were the unchanging, perfect archetypes behind the messy, imperfect world of appearances, and the harmonies between these numbers governed everything from the vibrations of a plucked string to the majestic orbits of the celestial bodies. This conviction was born from a stunning discovery that bridged the abstract world of mathematics with the sensory world of sound. Tradition tells us that Pythagoras was passing a blacksmith shop when he was struck by the consonant, pleasing clangs of hammers striking metal. Intrigued, he investigated and found that the hammers producing these harmonious sounds had weights in simple, whole number ratios to one another. A hammer weighing twice as much as another produced a sound exactly 1 octave higher. The ratio of 2 to 1 created the most fundamental harmonic interval. Another pair with a ratio of 3 to 2 produced the perfect fifth. He then tested this principle on a monochord, a single-stringed instrument, and found that by pressing the string at points that divided it into these simple ratios, 1/2, 2/3, 3/4, he could reliably generate these same beautiful intervals. This was a revelation. A tangible, physical beauty was directly governed by an invisible mathematical law. This discovery of musical harmonics was the key that unlocked their entire worldview. If simple numerical ratios could produce something as sublime as musical harmony, then surely the entire cosmos must operate on similar principles. They imagined the planets, which they called the wandering stars, each moving in its own sphere around a central fire. As these spheres rotated, they too must produce a sound, a hum based on their orbital ratios. They reasoned that these celestial notes would combine into a magnificent, continuous chord, a music of the spheres. We cannot hear this cosmic symphony, they argued, only because it has been the constant background noise of our existence since birth. We are deaf to it in the same way a blacksmith becomes deaf to the clang of his own hammer. This was not merely poetic metaphor, but a serious scientific and philosophical proposition. The universe is a manifestation of mathematical relationships, and harmony is its fundamental language. Of course, the most enduring legacy of this school is the geometric rule that bears its name, the Pythagorean theorem. that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides, was likely known in some form to the Babylonians and Egyptians centuries earlier. But the Pythagoreans elevated it from a practical surveying trick into a profound cosmological principle. For them, it was not just about triangles, it was a universal law about the relationship between space and number. The theorem provided a method to quantify the world, to calculate any diagonal distance, to bridge the gap between the discrete world of counting and the continuous world of geometric form. It was a key that could unlock the dimensions of reality itself, proving that even the most fundamental shapes of our world were obedient to an underlying mathematical order. This obsession with numbers and their ratios, however, also led the Pythagoreans to a crisis that threatened to shatter their entire beautiful philosophy. It was the discovery of the irrational number, applying their own famous theorem to the simplest of right triangles, a triangle with two sides each of length 1. They found a terrifying result. The hypotenuse would be the square root of 2. To their horror, they proved that this number could not be expressed as a ratio of two whole numbers. It was a logos, meaning without ratio or inexpressible. Here was a length that clearly existed in the geometric world, a definite distance you could point to, yet it was impossible to represent with the very whole numbers they considered divine. This was a devastating paradox, so threatening to their core beliefs that legend claims they drowned the member of their cult who first revealed this secret to the outside world. Yet, this apparent flaw in their perfect mathematical universe was in fact their greatest gift to the future of science. The Pythagorean school's ultimate contribution was not a specific theorem but a foundational mindset, the conviction that the universe is comprehensible because it is written in the language of mathematics. This core belief that nature's laws can be described by mathematical equations and geometric models is the unspoken assumption behind every scientific revolution that followed. It is the faith that guided Galileo when he declared that the grand book of the universe is written in the language of mathematics. It is the principle that enabled Newton to formulate his law of universal gravitation, and it is the same principle that allows modern physicists to search for a theory of everything using esoteric equations. The Pythagoreans were the first to dream of a fully quantifiable cosmos, and in doing so, they laid the philosophical groundwork for the entire scientific enterprise, transforming the world from a realm of capricious gods into a puzzle of elegant, solvable numbers. While the Pythagoreans were searching for cosmic harmony in numbers, another intellectual giant was constructing a comprehensive system to explain the entire natural world through observation and categorization. Aristotle, a student of Plato and tutor to Alexander the Great, approached the universe not as a mathematical abstraction, but as a living, changing reality to be understood through careful study. His physics, which dominated Western thought for nearly 2,000 years, was built on a few core principles that, while we now know them to be flawed, provided the first complete and systematic framework for asking why things happen in the physical world. Central to this system were his concepts of motion and his doctrine of the four causes. Aristotle classified all motion into two fundamental types: natural motion and violent motion. Natural motion was an object's innate tendency to move toward its natural place in the cosmos. He believed the universe was composed of concentric spheres with the heavy, imperfect Earth at the center. Therefore, the natural motion of a heavy object like a rock was to fall straight down toward the center of the universe. The natural motion of a light substance like smoke or fire was to rise upward toward its own sphere. Anything else, a rock thrown, an arrow shot from a bow, was considered violent motion, requiring a continuous force to sustain it. This is why he believed that an arrow kept flying, because the air displaced by its head rushed around behind it to push it forward. The idea that an object in motion would simply stay in motion unless acted upon by a force, a cornerstone of Newtonian physics, was alien to his worldview. This explained the observable world well enough. A cart stops moving when the horse stops pulling it, but it completely missed the concept of inertia. To answer deeper questions about existence and change, Aristotle developed his famous theory of the four causes, a multi-layered framework for understanding why anything is the way it is. Imagine a bronze statue. The material cause is the bronze itself, the raw substance from which it is made. The formal cause is its specific shape or design, the blueprint of the statue in the sculptor's mind. The efficient cause is the act of the sculptor hammering and shaping the metal, the agent that brings it into being. And finally, the final cause is the statue's ultimate purpose or end goal, to honor a deity or to serve as a decoration. For Aristotle, a complete explanation of any phenomenon, from an acorn growing into an oak tree to a state being governed, required understanding all four of these causes. The acorn's material cause is its organic matter, its formal cause is the essence of an oak tree, its efficient cause is the nutrients and sunlight that nourish it, and its final cause is its purpose, to become a fully mature oak. This teleological view that everything in nature has a purpose or final end was a powerful and deeply influential way of seeing the world as inherently meaningful and directed. This entire physical system was integrated with his theory of the five elements, an expansion of earlier ideas. Beneath the sphere of the moon was the terrestrial realm, composed of four mutable and changeable elements: earth, water, air, and fire. Each sought its natural place, creating a layered world with earth at the bottom, then water, then air, and fire at the top. Beyond the moon was the celestial realm, a region of perfection and eternal circular motion, made of a fifth, unchanging element, the ether. This comprehensive model provided answers. It explained why stones fall and flames rise, why the heavens are perfect and unchanging, and why everything in the sublunar world is subject to generation and decay. While ultimately replaced by the mechanical universe of Newton and Galileo, Aristotle's physics was a monumental achievement in systematization. It created a common language and a set of questions that natural philosophers would wrestle with for centuries, and the very process of dismantling its inaccuracies was a powerful engine that drove the scientific revolution forward. Yet, if Aristotle's physics was the grand, flawed edifice, his creation in another field was the indestructible foundation upon which all rational inquiry, including modern science, would be built. This was his development of formal logic, a set of rules for distinguishing valid reasoning from fallacious argument, which he compiled in a collection of works known as the Organon, or tool. Before Aristotle, while people certainly reasoned and argued, there was no systematic study of the structure of argument itself. He was the first to analyze and codify the patterns of sound thinking, providing humanity with its first instruction manual for the proper use of reason. The centerpiece of this system was the syllogism, a form of deductive reasoning that guarantees a conclusion if its premises are true. The most famous example is all men are mortal. Socrates is a man, therefore Socrates is mortal. The power of the syllogism lies in its form, not its content. The structure itself ensures that if you accept the general premise and the specific case, the conclusion is inescapable. Aristotle meticulously classified different types of syllogisms, identifying which forms were valid and which were not, and he explored the relationships between categories and statements in a way that had never been done before. This was akin to inventing the rules of grammar for the language of rational thought. It provided a method to move with certainty from what is already known to new, hidden truths, a process essential for constructing any scientific theory. This toolkit of logic became the invisible backbone of the scientific method, while the experimental and observational aspects of science developed later. The logical framework for constructing a hypothesis, drawing inferences, and testing for contradictions is pure Aristotelian logic. A scientist forms a hypothesis, which is a kind of premise. They then deduce what observable consequences must follow if that hypothesis is true. This is the logical conclusion of the syllogism. They then perform an experiment or make an observation to see if those predicted consequences actually occur. If the results contradict the logical deduction, the original premise, the hypothesis must be revised or discarded. This cyclical process of hypothesis, deduction, and testing is a direct application of the principles Aristotle laid down in the Organon. He gave science its essential grammar, the rules for building a coherent and testable argument about the world. In doing so, Aristotle provided the intellectual scaffolding that would allow later minds, from Newton to Einstein, to construct their own revolutionary theories, proving that while his physics could be superseded, his logic was and remains timeless. This radical shift in perspective brings us back to the very dawn of Western philosophy and science, to a bustling port city in Ionia called Miletus, and to a man named Thales. Living in the 6th century before the Common Era, Thales occupies a unique and monumental position in history. He is often celebrated as the very first philosopher, the individual who took that crucial initial step away from explaining the world through the whims of gods and toward explaining it through observable natural principles. And his central proposal, while seemingly simple, contained a seed of such profound implication that it effectively marks the origin of theoretical physics. He declared that the fundamental substance, the archicircumflex or the originating principle of all things, was water. Now, on its surface, the choice of water might seem almost quaint, a naive guess from a less sophisticated time. But to dismiss it on those terms is to miss the entire point and the staggering genius of the proposition. The true revolution was not in the specific selection of water, but in the underlying act of reasoning itself. Thales was looking at the incredible diversity of the world, the solid earth, the flowing rivers, the burning fire, the breathable air, the flesh of animals, the leaves of trees, and he asked a revolutionary question. Beneath all this apparent variety, could there be a single, unified stuff that takes on different forms? He was searching for a unity in nature, a principle of simplicity underlying the overwhelming complexity we perceive with our senses. This concept of a fundamental substance from which everything else is derived is known as material monism, and Thales was its first proponent. So why did he settle on water? His reasoning was likely grounded in careful observation of the natural world, not in myth or superstition. He would have seen that water is essential for life. Without it, plants, animals, and humans wither and die. He observed water's unique ability to exist in 3 distinct states: as a solid ice, as a liquid flow, and as a vaporous mist or steam. This transformative quality made it a compelling candidate for a primary substance. It could mimic the solidity of earth, the fluidity of air, and the energetic nature of fire. He may have also noted that the earth itself, in the geography known to him, appeared to be largely surrounded by and saturated with water. The fecundity of river deltas, the presence of moisture in all living things, and the way water could both nourish and destroy, all pointed to it as a primary generative force. To understand the sheer magnitude of this intellectual leap, we have to contrast it with the prevailing worldview of his time. The dominant explanations for cosmic origins were mythological, like the Greek story of chaos giving birth to Gaia and Uranus. These were narratives of personification and divine conflict, where the world was shaped by the desires and struggles of anthropomorphic deities. Thales deliberately stepped away from this tradition. He was not asking which god made the world, he was asking what the world is fundamentally made of. He shifted the question from who to what, and in doing so, he reoriented the entire project of human understanding. He replaced the capriciousness of divine will with the consistency of natural law, suggesting that the universe operates on principles that can be observed, reasoned about, and understood by the human mind. This move from mythos to logos, from story-based explanation to reason-based inquiry, is arguably the most important intellectual transition in human history, and Thales stands at its very beginning. He set a precedent that every scientist and philosopher after him would follow. The universe is rational and comprehensible. His proposition that a single material principle could explain the totality of existence is the direct ancestor of every unifying theory in modern physics. The search for a theory of everything in contemporary physics, the quest to unify the laws of the very large and the very small under a single mathematical framework, is the modern expression of the very same impulse that drove Thales. He was looking for the cosmic watermark, the one thing that, in its various arrangements, gives rise to the spectacular panorama of reality. While we now look to quantum fields or vibrating strings, we are walking the path that Thales first dared to imagine, a path that begins with the audacious faith that the complex world can be explained by a simple, underlying truth. While Aristotle's cosmos was a plenum, a continuous and seamless whole with no room for emptiness, a dissenting voice from his own intellectual lineage dared to challenge this core assumption. A few generations after Aristotle, Strato of Lampsacus, who became the third head of the Lyceum, looked at the same natural world and saw something entirely different. He became the first major philosopher to systematically argue for the existence of a void, not just as an abstract possibility, but as a physical reality woven into the very fabric of matter. His theory was a direct affront to the Aristotelian doctrine that nature abhors a vacuum, and it was built not on pure speculation, but on a series of clever and observable physical phenomena. Strato's reasoning began with the simple act of observation. He noted that when light passes through a window into a darkened room, it doesn't push the air out of the way. The particles of light seem to slip between the gaps in the air itself. Even more persuasively, he considered what happens when you submerge a pot in water. If the pot is solid, the water cannot enter. But if the pot is a hollow, inverted jar, bubbles of air escape as water rushes in to fill the space. Strato argued that this water isn't just pushing the air aside. It is moving into a space that was previously occupied by the air that left. This implied that within the jar there were, for a fleeting moment, tiny pockets of true emptiness between the exiting air and the entering water. He also observed that when we breathe, air seems to flow into our lungs effortlessly, suggesting it moves into a pre-existing empty space within our bodies that expands to draw it in. For Strato, these everyday occurrences were not minor curiosities. They were proof that microscopic voids exist within and between all substances, allowing for compression, movement, and the flow of matter. This was a monumental shift in thinking. Aristotle had argued that motion through a void would be impossible because with no resisting medium, an object would move at infinite speed, a logical absurdity in his view. He believed that a medium like air or water was necessary to provide resistance, which also explained why different objects fall at different rates. Strato, however, turned this logic on its head. He proposed that in a true void, with no air resistance at all objects would fall at exactly the same rate. He likely came to this conclusion by observing that a thin piece of cloth and a heavy stone, when dropped from a great height, don't seem to differ in speed as much at the very beginning of their fall. It is the resistance of the air that eventually causes the divergence. This insight was a stunning prefiguration of Galileo's famous, though likely apocryphal, experiment at the Leaning Tower of Pisa. Strato was laying the essential groundwork for the concept of a uniform gravitational acceleration independent of mass. The implications of this void theory were profound, especially for the long-dormant atomic theory of Democritus. Democritus had argued that atoms moved through an infinite void, but he lacked a physical mechanism to explain why they moved or how a void could be proven. Strato provided that physical evidence. His observations of compression and flow gave the atomic theory its missing mechanical foundation. If voids exist between particles of matter, then it becomes possible to explain how objects can be compressed, like squeezing a sponge, or how different densities are possible. A heavy, solid block of lead contains less void space than a light, porous piece of wood. This idea of matter being mostly empty space is a cornerstone of modern physics, and Strato was the first to build a compelling, observation-based case for it. His ideas did not die with him. They found a brilliant and practical successor in Hero of Alexandria, an engineer and mathematician who lived in the 1st century of the Common Era. Hero took Strato's concept of the void and demonstrated its power with spectacular inventions. His most famous device, the eolipile, was a primitive steam engine that relied on the forceful expulsion of steam and air. But his work with pneumatics and siphons truly showcased the void in action. Hero constructed devices that seemed to magically make water flow uphill or wine pour from a sealed container. The secret was atmospheric pressure. He understood that by creating a vacuum inside a vessel, the pressure of the outside air would force a liquid to move into that empty space. These were not just party tricks, they were practical demonstrations of a physical principle that Aristotle had declared impossible. Hero was proving the existence and utility of the void through engineering, giving tangible, working models that validated Strato's theoretical insight. The legacy of Strato's void is a story of an idea lying dormant, waiting for the right conditions to flourish. During the scientific revolution, as the Aristotelian worldview began to crumble, thinkers like Evangelista Torricelli and Blaise Pascal were grappling with the same problems of air pressure and vacuums. When Torricelli inverted a tube of mercury in a basin and saw the column of liquid drop, leaving an empty space at the top, the first artificially created, sustained vacuum, he was confirming what Strato had argued centuries before. Pascal's famous experiment carrying a barometer up a mountain, showing that air pressure decreases with altitude, further demonstrated that we live at the bottom of an ocean of air that exerts a force that only makes sense if a vacuum can exist to create a pressure differential. The intellectual thread connecting these revolutionary experiments leads directly back to the Lyceum and the keen observations of Strato of Lampsacus, the first philosopher to look at the solid world and see the invisible spaces that make motion and change possible. While these thinkers were speculating about the fundamental structures of the cosmos, a more practical and life-saving insight was emerging from the Roman Republic, one that addressed a threat far closer to home. In the 1st century before the Common Era, a prolific scholar and polymath named Marcus Terentius Varro was compiling a comprehensive guide to farming. In his work on agriculture, amidst advice on soil quality and livestock breeding, he included a warning so perceptive it seems to belong to a different era entirely. He advised landowners to avoid building their villas in the vicinity of swamps, and his reasoning had nothing to do with bad air or evil spirits, the common explanations of the time. Instead, he wrote that in certain marshy places, there are bred certain minute creatures which cannot be seen by the eyes, but which float in the air and enter the body through the mouth and nose and cause serious diseases. Just pause and consider the sheer brilliance of that statement. Over 1900 years before Louis Pasteur and Robert Koch would definitively prove the germ theory of disease, a Roman scholar had already connected the dots. He gave these invisible agents a name, Animalia Minuta, or tiny little creatures. He understood they were airborne, that they entered the body through specific pathways, and that their presence was linked to a particular damp environment. This was not a vague superstition. It was a rational, proto-scientific hypothesis based on observable correlations between swampland and illness. Varro was looking at the world and proposing a physical, biological cause for sickness that operated beyond the limits of human sight, a truly revolutionary leap in medical thought. To grasp the full weight of this idea, you have to understand the dominant medical paradigms of Varro's time. The most influential theory imported from Greece was the miasma theory. This concept held that diseases like malaria, whose name literally means bad air, were caused by breathing in foul, corrupted vapors emanating from rotting organic matter in swamps or from polluted air in crowded cities. The miasma theory was compelling. It was based on sensory evidence. You could smell the stench of a swamp, and you could observe that people who lived near such places often fell ill. The solution, therefore, was to avoid these bad smells or to carry fragrant herbs to counteract them. Varro's theory was fundamentally different. He wasn't blaming an abstract, foul vapor. He was hypothesizing about living, microscopic organisms, a form of contagion that was particulate, not atmospheric. He was essentially suggesting that the problem wasn't the air itself, but what was carried within the air. So why was this brilliant insight lost for so many centuries? The primary reason is technological. Varro simply could not prove it. He had no microscope, no way to render these animalia minute visible and demonstrate their pathogenic power. Without the ability to provide empirical evidence, his idea remained an untestable and therefore unverifiable speculation. It was a philosophical suggestion buried in a farming manual, easily overshadowed by the more intuitive and sensorially supported miasma theory, which would continue to dominate medical thinking all the way through the Middle Ages and into the Renaissance. The authority of Galen, whose own work was based on humoral imbalances, further cemented a framework that left little room for invisible pathogens. Varro's proposal was a seed falling on stony ground, lacking the technological rain needed to make it sprout. The full flowering of his idea had to wait for the invention of the microscope in the 17th century. When Antony van Leeuwenhoek first turned his hand-ground lenses onto a drop of water and described a world of wriggling animalcules, he was providing the first visual confirmation that Varro's animalia minuta were real. Yet, even then, the connection to disease was not immediately made. It took another 2 centuries of painstaking work by pioneers like Pasteur, who disproved spontaneous generation and showed that microbes could spoil food and cause silkworm diseases, and Koch, who famously established his postulates to definitively link a specific microbe to a specific illness, for the germ theory to become the cornerstone of modern medicine. Varro had the correct conceptual framework but none of the tools to build upon it. His warning about swamps, it turns out, was precisely right. It was in such stagnant waters that the Anopheles mosquito, the vector for the malaria parasite, thrived. He correctly identified the environment of the danger, even if he couldn't identify the specific agent. The story of Varro's prescient idea is a powerful testament to the fact that a brilliant insight, without the means to validate it, can be centuries ahead of its time, lying dormant until technology finally catches up to the imagination. Now, let's consider a thinker whose evidence was not found in the stars or in abstract logic, but was quite literally beneath his feet. In the 6th century before the Common Era, the philosopher Xenophanes of Colophon was traveling through the mountainous regions of the Mediterranean when he made a startling discovery. Embedded high in the rocky cliffs far from any shore, he found the unmistakable imprints of seashells, the fossilized remains of fish and marine plants. Where others might have seen mere curiosities or the whimsical handiwork of the gods, Xenophanes saw a profound puzzle. How did the relics of an ocean come to be entombed on the summit of a mountain? His answer to this question was a stroke of genius that fundamentally reshaped humanity's conception of the Earth's history and its dynamic nature. Xenophanes reasoned that the only logical explanation was that the land he was standing on had not always been dry. Those mountaintops, he proposed, must have once been submerged beneath an ancient sea. He further suggested that over immense periods of time, the floor of that sea had been uplifted, becoming the dry land we see today. This was a radical departure from the prevailing views of a young and static Earth, a world created in its current form. He was proposing a planet in flux, subject to slow, colossal transformations on a scale that was almost unimaginable. He even speculated that this process was cyclical, that the Earth periodically underwent catastrophic shifts between sea and land, with the moisture from the oceans eventually evaporating and the whole cycle beginning anew. In a single, powerful inference drawn from a seashell, Xenophanes had introduced the concepts of geological change and deep time. To appreciate the sheer boldness of this idea, you have to consider the cultural context. The dominant creation myths, like the Greek story of a great flood sent by Zeus, often featured catastrophic, divine interventions that reshaped the world in a single, violent event. These were seen as singular moments in a relatively recent past. Xenophanes was replacing this divine, punctuated history with a natural, continuous process. He wasn't invoking a god's wrath to explain the shells on the mountain. He was invoking the slow, grinding work of natural forces over spans of time so vast they challenged human comprehension. He was looking at the Earth itself as an archive, and the fossils were its historical documents written in stone. This methodology makes him a pivotal, though often overlooked, figure in the history of science. Before him, explanations for the natural world were largely based on pure reason or theological narrative. Xenophanes introduced a third, crucial element: empirical evidence. He was one of the very first to use physical, observable clues from the natural world to reconstruct a past event. This is the fundamental principle of historical geology and paleontology. A modern geologist, upon finding marine fossils in a desert, would follow the exact same line of reasoning as Xenophanes, concluding that the region was once an ancient seabed that was later thrust upward by tectonic forces. He had discovered the Rosetta Stone for reading the Earth's biography, establishing that the planet has a history that can be decoded by studying the rocks and fossils it contains. The tragic reality, however, is that this foundational insight was another brilliant spark that was largely extinguished by the weight of later philosophical traditions. Aristotle's cosmology favored a stable and eternal Earth, and his immense authority helped suppress the notion of catastrophic change for centuries. The fossil evidence was often explained away within an Aristotelian framework. Some proposed that the shells had grown in the rocks through some mysterious formative power, or that they had been carried inland by massive floods. It wasn't until the Renaissance, when figures like Leonardo da Vinci independently observed fossils and argued forcefully against the idea that they were mere sports of nature, that Xenophanes' logic began to resurface. Leonardo, studying the fossil-rich hills of northern Italy, used the same evidence to make the same argument, completely unaware of his ancient predecessor. The full vindication of this ancient theory would eventually require the revolutionary work of James Hutton and Charles Lyell in the 18th and 19th centuries, who established the principles of uniformitarianism. The idea that the geological processes we see operating today are the same ones that shaped the Earth's deep past. When Hutton famously declared that he saw no vestige of a beginning, no prospect of an end, he was walking the path that Xenophanes had first illuminated over 2 millennia before, finally giving humanity the conceptual tools to grasp the awesome, abyssal depth of geological time. But while some were looking at seashells to understand the planet, a pioneering figure in southern Italy was performing a much more intimate kind of exploration, one that would fundamentally reshape our understanding of ourselves. In the bustling Greek colony of Croton around the 5th century before the Common Era, a man named Alcmaeon made a radical declaration that flew in the face of common sense and cultural tradition. Through careful dissection of animal bodies, he concluded that the seat of human intelligence, the very center of sensation and thought, was not the heart but the brain. This was a stunning claim, one that placed our consciousness not in the throbbing, emotionally resonant center of our chest, but in the silent, mysterious, and fragile tissue housed within our skulls. To grasp just how revolutionary this idea was, you have to consider what seemed intuitively obvious to almost everyone else. The heart is constantly in motion, its beat a relentless drum of life. We feel its rhythm quicken with fear, slow with calm, and pound with love or anger. It seemed directly connected to our deepest feelings and our very vitality. The brain, by contrast, was a cold, inert, and bloodless mass. It did not move, it did not seem to react. How could this passive organ possibly be the source of our thoughts, our dreams, and our reasoning? This cardiocentric view, the belief that the heart was the center of intellect, was not just a folk belief. It was a philosophical position championed by the most influential thinker of the ancient world, Aristotle himself. He argued that the heart was the first organ to form in an embryo, the warmest part of the body, and the obvious ruler of the physical self, with the brain serving merely as a radiator to cool the heart's passionate heat. Alcmaeon arrived at his counterintuitive conclusion not through philosophical speculation, but through the groundbreaking practice of empirical dissection. He was likely the first Greek to systematically dissect animal bodies for the purpose of scientific discovery, a methodology that was centuries ahead of its time. As he traced the pathways of the senses, he made a critical observation. He discovered delicate, white, cord-like structures leading from the sensory organs, the eyes and the ears, directly into the brain. He called these structures poroi, or channels. He logically deduced that these were the pathways through which external sensations traveled, and since they all converged on the brain, it must be the central processing point where sight, sound, and smell were received and interpreted. He further reasoned that if the brain were physically damaged or shaken, sense perception and mental function were immediately impaired. An injury to the leg might cause a limp, but an injury to the head could rob a person of their memory, their speech, or their very mind. This direct physical evidence pointed unequivocally to the brain as the organ of cognition. This was a monumental shift from a philosophy based on feeling to a science based on observation. Alcmaeon was establishing a new kind of authority, the authority of anatomical evidence. He wasn't asking what felt like the center of thought. He was asking what physical structures in the body were connected to the act of sensing and thinking. In doing so, he effectively founded the discipline of neuroscience 2,400 years before the term even existed. He proposed that our mental life, our consciousness, was not a disembodied spirit but a function of a physical organ, a concept that is the absolute bedrock of all modern neurology and psychology. He was the first to suggest that to understand the mind, one must first understand the brain. The tragic irony of intellectual history is that Alcmaeon's correct, evidence-based theory was overshadowed for nearly 2,000 years by the immense authority of Aristotle's incorrect but intuitively appealing cardiocentric view. The Aristotelian paradigm, integrated into the works of Galen and later into medieval Christian and Islamic scholarship, became dogma. It shaped medical practice and philosophical thought for millennia, entrenching the idea of the passionate heart versus the rational mind in our very language. We still speak of learning something by heart or being broken-hearted, linguistic fossils of this ancient belief. It wasn't until the Renaissance, with the revival of anatomical dissection by figures like Andreas Vesalius and the later work of physicians like Thomas Willis, who literally wrote the first comprehensive book on the brain, Cerebri Anatome, that Alcmaeon's original insight was rediscovered and validated. The brain had to wait almost 2 millennia to be restored to its rightful place as the king of organs, a testament to how a brilliant empirical discovery can be lost when it conflicts with a more comfortable and authoritative philosophical tradition. As the intellectual revolution continued to unfold across the Greek world, a thinker named Anaximander arrived in Athens and brought with him a principle so fundamental it would one day become a law governing the entire physical universe. He looked at the world of constant change, the growth of a tree from a seed, the burning of a log into ash and smoke, and asked a profound question: when something appears to be created or destroyed, what is really happening? His answer was both simple and stunningly insightful. He declared that nothing ever truly comes into being from nothing, and nothing ever truly perishes into nothingness. Instead, all apparent creation and destruction is merely a process of mixing and separation. he called the fundamental ingredients of reality seeds, an infinite variety of tiny particles, and proposed that every substance contains a portion of every other. A piece of wood, for instance, contains particles of fire which are released and mixed with air when it burns, and particles of earth which remain behind as ash. What we perceive as the birth of a new thing or the death of an old one is just a rearrangement of eternal, uncreatable, and indestructible components. This doctrine is a direct, ancient precursor to the modern law of the conservation of mass, a cornerstone of both chemistry and physics formerly stated by Antoine Lavoisier in the 18th century. Lavoisier's famous experiment, where he carefully measured the mass of materials before and after a chemical reaction inside a sealed container, proved that the total mass remains constant. The substances change form, but the amount of matter stays the same. Anaxagoras arrived at this same profound truth not through precise measurement but through pure logical deduction. He reasoned that if something could come from nothing, then anything could appear at any time for no reason, which made the world unintelligible. For the universe to be a rational place that could be understood, there must be an underlying permanence beneath the surface flux. His seeds were that permanence, and his principle of mixture and separation was the mechanism of change. It was a philosophical argument for a universe governed by consistent, reliable rules. Anaxagoras's commitment to material, natural explanations didn't stop at the Earth's surface. He fearlessly applied it to the heavens as well, with explosive consequences. At a time when the sun and moon were widely worshipped as deities, he made two bold physical claims. First, he declared that the sun was not the chariot of the god Helios, but was in fact a gigantic, incandescent mass of molten rock, larger than the entire Peloponnese. Second, he correctly identified that the moon does not produce its own light, but rather shines by reflecting the brilliant light of this fiery solar rock. He even used this understanding to provide the first correct explanation for lunar eclipses, proposing that they occurred when the Earth moved between the sun and the moon, casting its shadow upon the lunar surface. This was not just a scientific advancement, it was a theological earthquake. By demoting the celestial bodies from gods to physical objects, Anaxagoras committed an act of impiety in the eyes of his fellow Athenians. His naturalistic cosmology directly challenged the state-sponsored religious traditions, and he was put on trial for his ideas. He was ultimately forced to flee Athens, becoming one of history's first martyrs for scientific truth. His persecution highlights the immense culturl Chinese letter of moving from a world dominated by divine agency to one governed by impersonal natural law. Yet his courage cemented a crucial legacy. The heavens were not a separate, sacred realm, but part of the same physical cosmos as the earth, subject to the same rational inquiry. This desacralization of the cosmos was an essential step on the long road to modern astronomy, proving that the pursuit of truth about the natural world often requires challenging the deepest held beliefs of a society. Just as the bold ideas of Anaxagoras faced persecution for a materialistic view of the cosmos, another school of thought would later emerge, refining these concepts into a comprehensive and comforting philosophy for living. In the wake of Alexander the Great's conquests, as the Greek world grew larger and more chaotic, a philosopher named Epicurus established his school, known as the Garden, offering a radical alternative to the anxieties of the age. His system, Epicureanism, was built upon a single, powerful foundation, the atomic theory of Democritus. But Epicurus and his later Roman poetic champion, Lucretius, did far more than just repeat an old idea. They transformed it into a complete worldview that banished the fear of gods and death, presenting a universe operating solely on the principles of atoms and the void. Epicurean physics begins with two unwavering principles: nothing ever comes from nothing, and nothing ever returns to nothing. This echoes Anaxagoras, but Epicurus gave it a specific mechanical engine, the atom. He argued that the universe consists of only two fundamental and eternal realities: an infinite number of solid, indestructible atoms and an infinite void, the empty space through which these atoms move. Everything we see, from the hardest rock to the most ethereal soul, is merely a temporary congregation of these atoms. The gods, should they exist at all, were themselves composed of finer atoms and lived in a state of perfect tranquility in the spaces between worlds, completely unconcerned with human affairs. They did not create the universe, they did not answer prayers, and they certainly did not punish souls in an afterlife. This was a universe free from divine meddling, a vast, impersonal machine whose workings could be understood through reason alone. One of Epicurus's most ingenious contributions was his solution to a problem that had troubled atomism from the start. If all atoms simply fell downward in the void at the same speed, following a strict parallel path, how could they ever collide and form the complex structures of our world? They would fall forever, ships passing in the night, never interacting. Epicurus introduced a brilliant and tiny modification to this model. He proposed that atoms, as they fall, occasionally and spontaneously undergo a minute uncaused swerve. He called this the clinamen, a barely perceptible deviation from their straight downward path. This infinitesimal swerve was just enough to cause a collision with a neighboring atom, setting off a chain reaction of impacts and entanglements that eventually gave rise to stars, planets, and living beings. This wasn't a physical law as we understand it today. It was a philosophical necessity to introduce an element of freedom and spontaneity into a deterministic cosmos. It was the atomic seed of chance that made our ordered world possible. This entire philosophical system, which might have been lost to the book burnings of later eras, was preserved for posterity in one of the most magnificent poems ever written, De Rerum Natura, or On the Nature of Things, by the Roman poet and philosopher Titus Lucretius Carus. Living in the 1st century before the Common Era, Lucretius took the dense, technical prose of Epicurean doctrine and transmuted it into soaring Latin hexameter verse. His mission was therapeutic. He sought to liberate humanity from what he saw as its two greatest sources of misery: the fear of the gods and the terror of death. His poem is a sustained argument, using the beauty of its own language to demonstrate the beauty of a materialistic cosmos. He walks the reader through the atomic nature of everything, from the hardy crust of the earth to the invisible films of atoms that peel off objects to create vision, explaining sensation and thought as purely physical processes. Lucretius's descriptions often reach a level of insight that feels startlingly modern. He argues that the universe must be boundless, asking a profound question. If you were to travel to the very edge of space and throw a spear, where would it go? It must either fly onward, proving there is more space, or hit some barrier which would itself have an other side. Therefore, space and the number of atoms within it must be infinite. Even more remarkably, he applies atomic principles to the living world in a way that prefigures evolutionary theory. He describes a primordial earth teeming with strange and monstrous creatures, odd combinations of limbs and organs that were not fit to survive. Those that could not find food or reproduce perished, while those whose atomic constitutions were accidentally suited to their environment endured and propagated. He writes of centaur-like creatures that could not have existed because the atomic natures of man and horse mature at different rates, showing a keen sense of biological compatibility. This is not natural selection with its mechanistic driver of genetic inheritance, but it is a powerful vision of a world where life forms are tested by their environment and only the functionally fit persist. For over a millennium, the radical materialism of Epicurus and the sublime poetry of Lucretius were largely suppressed, surviving in just a handful of fragile manuscripts tucked away in isolated monastic libraries. The prevailing philosophies of Stoicism, and later the theological dominance of Christianity, viewed their godless universe as a profound threat. But then, in the early 15th century, a Renaissance book hunter named Poggio Bracciolini made one of the most significant discoveries in the history of ideas. In a remote German monastery, he unearthed a complete copy of Lucretius's On the Nature of Things. The rediscovery of this text sent shockwaves through the intellectual world of Europe. Here was a fully formed, ancient, and persuasive argument for a universe without divine providence, a world explained by natural laws. Renaissance thinkers grappling with the text found themselves confronted with ideas that would directly fuel the scientific revolution. The concept of an infinite universe challenged the cozy, finite cosmos of medieval scholasticism. The idea that all phenomena, including the human soul, had a physical basis encouraged a new focus on direct observation and mechanical explanation. Figures like Giordano Bruno, who was burned at the stake for his cosmological visions, drew directly on Lucretian infinity. Galileo's focus on matter and motion, his insistence on describing the physical world mathematically, resonates with the Epicurean focus on a knowable material reality. Even Isaac Newton, though he believed in a creator God, constructed a universe that, in its day-to-day operations, was a giant clockwork machine running on impersonal forces, a vision far closer to the atomic void of Epicurus than to the purpose-driven cosmos of Aristotle. The atomic theory, kept alive by this philosophical and poetic masterpiece, was no longer just a speculation. It was a catalyst providing the intellectual courage for a new generation to see the world as it is, a vast and beautiful dance of particles in an infinite space. While the intellectual giants of Athens and Alexandria were shaping our understanding of the earth and the heavens, an astronomer working in the bustling Hellenistic city of Seleucia on the banks of the Tigris River was piecing together a connection between the two that was centuries ahead of its time. Seleucus of Seleucia, active in the 2nd century before the Common Era, is a figure shrouded in some mystery, but his surviving ideas reveal a mind of extraordinary synthesis. He stands as one of the very few in the ancient world who actively championed the heliocentric theory of Aristarchus, and he went even further. He looked at the regular, ceaseless ebb and flow of the ocean tides and dared to propose a physical link to the distant, silvery moon, offering a stunningly prescient explanation that pointed toward the concept of a universal, attractive force. To understand the sheer novelty of Seleucus's theory, we need to consider the other explanations for the tides that were circulating in the ancient world. The most dominant theory put forward by figures like Posidonius was that the tides were the oceans breathing, a kind of vast pulmonary motion driven by the earth itself, perhaps influenced by subterranean currents or the spirit of the world. Others believed they were caused by the gravitational pull of the sun alone, or by the mingling of freshwater rivers with the saltwater sea. What was consistently missing was the key actor that Seleucus correctly identified, the moon. He observed that the tides were not random. They followed a predictable pattern that was synchronized with the lunar cycle. High tides occurred not just once but twice a day, and their intensity varied with the phases of the moon, reaching their peak during the new and full moon. This precise correlation was his crucial clue. Seleucus proposed that this was not a mere coincidence but evidence of a physical interaction. He suggested that the moon, in its orbit around the Earth, exerted a kind of attractive power or influence on the waters of the ocean, literally pulling them toward it. As the Earth rotated, this bulge of water would follow the moon's position, creating the rhythmic rise and fall of the tides. He even understood the amplified tides during syzygy, the alignment of the sun, earth, and moon, reasoning that the sun's own, lesser attractive force combined with the moon's at these times to create a greater pull. This was a monumental leap. He was proposing that a celestial body could exert a physical force across the vast, empty void of space to affect something on Earth. This idea of action at a distance was a radical departure from the prevailing Aristotelian physics, where objects could only be moved by direct contact or by seeking their natural place. The true significance of Seleucus's tidal theory lies in its role as a direct, if incomplete, precursor to Newton's law of universal gravitation. Seleucus lacked the mathematical framework to quantify this force. He had no concept of an inverse square law or the precise mechanics of orbital motion. What he possessed was the fundamental physical insight that the same force which might hold the moon in its orbit could also be the very one tugging at our oceans. He was attempting to unify celestial and terrestrial phenomena under a single physical principle, a core ambition of modern physics. He saw the cosmos not as a series of separate, disconnected realms, but as an interconnected system where the same laws applied everywhere. His work represents one of the earliest recorded attempts to find a unified physical law governing the entire universe. Tragically, the legacy of Seleucus, like that of Aristarchus, was another brilliant dead end. His writings have been almost entirely lost, and we know of his ideas only through references and criticisms by later writers, particularly in the works of the Greek historian Plutarch and the Babylonian astronomer Sextus Empiricus. In a world still dominated by Aristotelian thought, his theories of a moving earth and a moon pulling the seas were seen as outlandish. The intellectual momentum was not with him, and his profound insights were buried under the weight of a geocentric, element-based cosmology. It would take nearly 1800 years for the puzzle of the tides to be picked up again with the same clarity of thought, when Galileo, despite his own incorrect theory involving the Earth's motion, and later Newton with his magnificent synthesis, would finally provide the mathematical proof for the gravitational connection that Seleucus had so brilliantly perceived. His story is a poignant reminder of how fragile the thread of scientific progress can be, and how a solitary voice, armed with keen observation and logical deduction, can glimpse a truth that his own civilization is not yet ready to hear. Yet while Seleucus was gazing at the moon's pull on the tides, another civilization was achieving a level of medical sophistication that would not be rivaled in the West for over 1,000 years. In the fertile plains of the Indian subcontinent around the 6th century before the Common Era, a physician known as Sushruta was compiling a body of knowledge so vast and detailed it would become the cornerstone of Ayurveda, the science of life. His work, the Sushruta Samhita, is not merely a collection of remedies. It is a comprehensive, systematic medical encyclopedia that presents a breathtakingly empirical and procedure-based approach to healing, establishing foundational principles for clinical practice and surgery that feel astonishingly modern in their rigor and insight. What sets the Sushruta Samhita apart is its profound commitment to a systematic methodology. The text meticulously classifies diseases, carefully distinguishing between those that are medical, requiring treatment with herbs and diet, and those that are surgical, requiring the intervention of a blade. It describes the causes and symptoms of over 1,000 distinct ailments, from fevers and skin conditions to diabetes and heart disease, and it catalogues the properties and uses of over 700 medicinal plants. But the true revolutionary heart of the work lies in its sections on surgery, or Shalya Tantra. Sushruta didn't just see surgery as a last resort, he viewed it as a noble and essential branch of medicine, one that required its own specialized knowledge, meticulous training, and a profound understanding of the human body. He established a formal curriculum for aspiring surgeons, outlining a step-by-step process of learning that began with theory, moved to practical exercises on inanimate objects like fruits and water skins, progressed to dissection on cadavers, and only then culminated in supervised procedures on patients. This structured, graduated approach to surgical education is a direct precursor to the modern system of medical residency. The text's most enduring legacy is its breathtakingly detailed catalogue of surgical instruments and procedures. Sushruta described 125 different surgical tools crafted from iron, steel, wood, and bone. These were not crude implements, they were specialized devices designed for specific tasks. He detailed probes, scalpels, lancets, specula for examining wounds, and a variety of forceps, including some for extracting foreign objects and others for clamping blood vessels. The sophistication is staggering. He described the use of tubular leeches made of horn to drain fluids, a primitive form of suction, and he even outlined the proper way to test the sharpness of a blade on a hair. With these instruments, he documented complex operations that were unimaginable elsewhere in the ancient world. The removal of bladder stones and cataracts, the repair of intestinal obstructions, and even the draining of fluid from the brain in cases of hydrocephalus. Perhaps the most famous and visually compelling evidence of this advanced surgical knowledge is the text's detailed description of rhinoplasty, the reconstruction of a nose. In an era where amputation of the nose was a common punishment, Strato developed a technique to restore the feature. His method was both ingenious and anatomically sound. He instructed the surgeon to cut a patch of living flesh from the patient's own cheek, carefully leaving one end attached to ensure a blood supply. This flap of skin was then twisted and grafted onto the stump of the nose, with two hollow tubes made from a plant stem inserted into the nostrils to maintain their shape and allow for breathing during the healing process. This procedure, which involved principles of tissue viability, plastic reconstruction, and post-operative care, was successfully performed in India for centuries before it was rediscovered by British colonial surgeons in the 18th century, who were utterly amazed by its sophistication and brought the technique back to Europe, where it became known as the Indian method. Beyond the specific techniques, the Sushruta Samhita established core clinical principles that remain vital to medicine today. Sushruta emphasized the critical importance of pre-operative care, including cleansing the patient, preparing the surgical theater, and ensuring proper lighting and positioning. He discussed the management of pain using wine and herbal sedatives, an early form of anesthesia. He provided exhaustive instructions for post-operative wound management, describing the use of antiseptic pastes made from herbs like turmeric and honey to prevent infection and promote healing, an intuitive understanding of antimicrobial properties long before the germ theory was established. He even classified bones and joints, described the major muscles, and identified 107 vital points or marmers, where injuries could be particularly dangerous, showing a deep appreciation for anatomy. The text's holistic, systematic, and empirical approach, rooted in observation, procedure, and a profound respect for the healer's art, created a legacy of clinical excellence that stands as one of the most stunning achievements of the ancient scientific world. While the torch of precise celestial knowledge flickered and at times seemed to dim in the West, it was burning with extraordinary brightness on the other side of the world. In the 5th century of the Common Era, in the heart of the Gupta Empire in India, a young mathematician and astronomer named Aryabhatta produced a work of such staggering insight that it would lay the foundations for a uniquely mathematical approach to understanding the cosmos. His masterpiece, the Aryabhatiya, written when he was just 23 years old, is a concise but explosive text that tackles the grandest astronomical questions with the cool, precise language of numbers and equations. In its pages, we find a mind that was not content with philosophical speculation, but was driven to calculate, to predict, and to model the heavens with a level of mathematical rigor that was centuries ahead of its time. Perhaps his most revolutionary and immediately graspable idea was his assertion about our own planet's motion. At a time when the dominant view, both in India and across the classical world, was of a stationary Earth around which the entire universe turned, Aryabhatta proposed something that must have seemed absurd to his contemporaries. He correctly stated that the daily rising and setting of the stars and planets is not due to their motion around us, but is an illusion created by the Earth's own constant rotation on its axis. He used a beautifully simple analogy to explain this. Just as a passenger in a boat moving along a river sees the stationary trees on the bank appear to move backward, so too do we on this rotating Earth see the fixed stars appear to wheel across the sky. This was a profound act of intellectual reorientation. He was shifting the frame of reference from a human-centered cosmos to a physically realistic one, understanding that the most obvious sensory evidence, that we stand still, could be a grand and persistent illusion. This was not his only challenge to the cosmological orthodoxy. While his system was not purely heliocentric in the way Aristarchus had envisioned, Aryabhatta took a monumental step in that direction. He proposed that the Earth not only spins but also revolves around the Sun, and that the Moon and the planets shine by reflecting sunlight. He described the orbits of the planets relative to the Sun, a concept that greatly simplified their otherwise bewildering and erratic paths across the sky as seen from Earth. To make this model work, he needed more than just a bold idea. He needed precise data. And so, with the tools of trigonometry and algebra that he helped pioneer, he set out to measure the world and the heavens. He calculated the Earth's circumference, arriving at a figure of 24,835 miles, a value that is less than 1% off from the modern measurement of 24,901 miles. This was a feat of computation rivaling that of Eratosthenes, but achieved through different methods and from another corner of the globe, confirming the spherical nature and size of our planet through independent, brilliant calculation. The true, enduring genius of Aryabhatta, however, lies not in any single claim, but in his overarching methodology. He fundamentally transformed astronomy from a descriptive science into a predictive, mathematical one. He didn't just say the Earth rotated, he provided the mathematical framework to understand its motion. He didn't just suggest eclipses were caused by shadows, he calculated their timing, duration, and the precise mechanics of their occurrence with remarkable accuracy. He computed the length of the solar year, the sidereal year, and the relative periods of the planets, all with a commitment to numerical precision. He even provided sophisticated algebraic formulas and trigonometric tables to solve astronomical problems, treating the cosmos as a vast, ticking clockwork whose gears could be understood through the universal language of mathematics. This was the birth of computational astrophysics, an approach that saw the universe not as a realm of gods and spirits, but as a complex yet decipherable system of moving bodies governed by mathematical laws. His work stands as a towering monument to human reason, a bridge between ancient observation and the precise mathematical sciences that would eventually flourish across the world. Yet another brilliant idea was about to be lost, not to a lack of evidence, but to a fundamental misunderstanding of how we perceive the world itself. For 1,000 years, from the time of Plato and Euclid, the dominant explanation for vision was the emission theory, the idea that our eyes actively project a kind of visual fire or ray outward onto objects, allowing us to see them. It was an intuitive, almost egocentric view. Our gaze reached out and touched the world. But in the 11th century, a revolutionary thinker working in Cairo's bustling intellectual center systematically dismantled this ancient belief and, in the process, established a new standard for how science itself should be conducted. His name was Abu Ali al-Hasan ibn al-Hasan ibn al-Haytham, known in the West as al-Hazan, and his work on light and vision didn't just create a new field of study, it gave us the scientific method. Ibn al-Haytham's journey to this breakthrough was dramatic. Born in Basra, his intellect earned him a position as a vizier, but he fell out of favor with the mercurial Fatimid Caliph al-Hakim. Fearing for his life, Ibn al-Haytham feigned madness and was placed under house arrest for a decade. It was in this forced isolation, cut off from public life, that he conducted the experiments that would change everything. With nothing but time, he turned his quarters into a laboratory, using dark chambers, light sources, and lenses to test every assumption about sight. His most powerful tool was the camera obscura, a dark room or box with a tiny pinhole in one wall. He observed that when light passed through this aperture, it projected an inverted image of the outside scene onto the opposite wall. This single phenomenon was devastating to the emission theory. If our eyes were emitting rays, the image in the camera obscura should be right side up. The only logical conclusion was that light travels in straight lines from the object through the pinhole and onto the surface. Vision, therefore, was not an active process of sending out rays, but a passive one of receiving light that is reflected from objects into our eyes. This led to his monumental rejection of the emission theory. He argued with impeccable logic that if the eye emitted rays, we should be able to see in the dark, and looking at extremely bright objects like the sun should not be painful. Furthermore, the afterimage we see after looking at a bright light, what we now call a retinal afterimage, proved that light had a physical effect on the eye, not the other way around. He proposed the intromission theory, that light is a physical entity that travels from luminous objects, reflects off of non-luminous ones, and enters the eye to form vision. He even correctly identified the parts of the eye involved, understanding that the lens was the crucial component for focusing these incoming rays, a principle that directly paved the way for the invention of eyeglasses and telescopes centuries later. But Ibn al-Haytham's genius extended far beyond this one correction. He was a master experimentalist who investigated the properties of light with a rigor that feels thoroughly modern. He studied reflection extensively, not just stating that the angle of incidence equals the angle of reflection, but proving it through painstaking experiment, laying the groundwork for the law of reflection. He then turned to the more complex phenomenon of refraction, the bending of light as it passes from one medium to another, like from air into water. He meticulously measured how a light ray bent when entering water or glass at different angles, compiling vast tables of data. While he couldn't derive the precise sine law that Snell and Descartes would later formulate, his experimental data was the essential raw material that made their discoveries possible. He explained why a stick looks bent in water and why pools appear shallower than they are, providing the first fully physical and mathematical account of these everyday illusions. Perhaps his most profound and enduring contribution, however, was not a specific discovery about light, but the process he used to make his discoveries. In his seminal work, The Book of Optics, he outlines a systematic approach to inquiry that reads like a modern scientific manual. He insisted that all scientific claims must be based on evidence gathered from controlled, repeatable experiments. He championed a cycle of skepticism, hypothesis, experimental testing, and mathematical verification. He railed against accepting the authority of ancient thinkers like Aristotle or Ptolemy if their claims did not match observable reality. This was a radical shift from a science based on philosophical reasoning to one based on empirical, experimental proof. He didn't just tell people how light worked, he showed them, providing the blueprints for others to replicate his findings. This methodology, hypothesize, test, verify, became the direct intellectual blueprint for the European pioneers of the scientific revolution. When Roger Bacon, Kepler, and later Galileo championed the experimental method, they were walking a path first clearly mapped out by Ibn al-Haytham during his long years of confinement, proving that sometimes the most expansive visions of reality are born in the smallest, darkest rooms. While brilliant minds like Ibn al-Haytham were revolutionizing our understanding of light, another towering intellectual figure from the Islamic Golden Age was turning his gaze downward, attempting to decipher the long, slow story written in the very rocks beneath our feet. Abu Ali al-Hussein ibn Abdullah ibn Sina, known in the West as Avicenna, was a true polymath whose medical encyclopedia, the Canon of Medicine, would dominate European universities for centuries. Yet his genius extended far beyond the human body. In his sprawling work, The Book of Healing, he dedicated a substantial portion to what we would now call earth sciences, and in doing so, he crafted a comprehensive theory of geology that was breathtakingly ahead of its time. He looked at a mountain range and saw not a static, permanent feature of the world, but a dynamic character in an epic narrative of planetary transformation. Avicenna's theories were grounded in a powerful blend of Aristotelian philosophy and his own meticulous first-hand observations of the natural world. He traveled extensively across Persia, and he couldn't help but notice the patterns in the landscape. He saw that mountains were often arranged in long, continuous chains, and that many of them were composed of distinct layers of rock, stacked one upon the other like the pages of a book. He observed that these layers often contained the same kinds of embedded seashells and other marine fossils, even when the mountains were located far inland and at tremendous heights. These observations led him to reject the still popular idea that fossils were mere sports of nature, odd shapes that coincidentally resembled life forms. With striking clarity, he asserted that fossils were, without a doubt, the actual remains of ancient aquatic animals. This was a crucial step as it transformed fossils from curiosities into historical documents, biological evidence of a world that no longer existed. His explanation for how these sea creatures ended up on mountaintops was a masterful synthesis of observation and logic, forming a coherent theory of mountain formation. Avicenna proposed that the land we walk on was not always solid. He envisioned a primeval earth where much of the current landscape was covered by a shallow, ancient sea. In these seas, sediments, mud, sand, and the shells of countless marine organisms slowly settled to the bottom, accumulating over immense periods to form thick, horizontal layers of rock. But then, a powerful earth-shaping force came into play. He suggested that subterranean winds or vapors generated by heat deep within the planet would occasionally try to escape. When these pent-up forces found a weak point in the Earth's crust, they would push upward, heaving these vast sedimentary layers into the air, tilting them, folding them, and finally cracking them to create the jagged peaks and valleys of mountain ranges. He called this process violent upheaval, and it was one of the first attempts to explain orogeny, the formation of mountains, through a natural physical mechanism rather than a single catastrophic divine event. This theory also provided him with a compelling explanation for another terrifying natural phenomenon, earthquakes. Rejecting mythological accounts that attributed quakes to the struggles of gods or giant creatures, Avicenna again turned to these subterranean forces. He reasoned that if trapped vapors and gases were powerful enough to slowly uplift entire mountain ranges over eons, then a sudden, explosive release of that same pent-up energy could easily shake the ground. He compared it to a pot of water boiling over. The building pressure eventually has to go somewhere, and when it does, it rattles the very container it's in. This was a remarkably prescient idea, a clear forerunner to the modern elastic rebound theory of earthquakes, which states that quakes are caused by the sudden release of stored strain along geological faults. While he didn't have the precise mechanics of plate tectonics, he correctly identified the core concept that the Earth's interior stores immense energy that can be violently released to reshape the surface. Perhaps the most profound implication of Avicenna's geology was its quiet, unstated embrace of deep time. His processes the slow accumulation of sediment grain by grain at the bottom of a sea, followed by the gradual, forceful uplift of those layers into mountains required spans of time that dwarfed human history and even the biblical chronology that was becoming dominant in the West. He was describing a world of almost unimaginable antiquity, a planet that had undergone slow, continuous change across millions of years. This stood in stark contrast to the prevailing Western view, which would be cemented a few centuries later, of a young Earth shaped by a single global flood. Avicenna's Earth was a dynamic, evolving system, not a static creation. Tragically, like so many of the advanced theories from the Islamic Golden Age, Avicenna's geological insights remained largely confined to the Eastern intellectual sphere. When his works were eventually translated into Latin, it was primarily his medical texts that captivated European scholars. His revolutionary ideas about mountains, fossils, and earthquakes were often overlooked or absorbed into less coherent frameworks. The full flowering of his geological thought had to wait for the 17th and 18th centuries, when European naturalists like Nicolaus Steno and James Hutton began to independently arrive at very similar conclusions. Steno's principles of stratigraphy, that rock layers are laid down horizontally with the oldest on the bottom, are a direct echo of Avicenna's observations. And Hutton's famous declaration that in geology, we find no vestige of a beginning, no prospect of an end, is the ultimate philosophical conclusion of the deep time that Avicenna's theories so clearly implied. In the mountains, Avicenna saw a history book, and in the fossils, he found its most compelling chapters, providing a systematic, naturalistic vision of a living, breathing planet long before modern geology was ever conceived. But that same spirit of rigorous, evidence-based inquiry was not confined to the study of optics or geology. Just a generation after Ibn al-Haytham, another colossal intellect emerged from the Islamic world who would perfect this methodology and apply it to an astonishing range of disciplines. Abu Rayhan al-Biruni, born in the year 973 in what is now Uzbekistan, was a polymath in the truest sense, an astronomer, geographer, anthropologist, historian, and physicist all in one. What truly set him apart, however, was not merely the breadth of his knowledge, but his profound and self-conscious philosophy of how knowledge itself should be acquired. He cultivated a scientific ethos so rigorous, so skeptical, and so systematic that it stands as a near-perfect blueprint for the modern scientific method centuries before the term was ever coined. Al-Biruni's core philosophy can be distilled into a single, radical principle. All knowledge, regardless of its source, must be subjected to doubt and verified through direct observation and experiment. He was fiercely critical of blind acceptance, whether it was of ancient Greek authorities like Aristotle or of the traditional beliefs of his own culture. In his own words, he warned that the seeker after truth is not he who studies the writings of the ancients and, following his natural disposition, puts his trust in them, but rather he who suspects his faith in them and questions what he gathers from them. This was more than just a suggestion, it was the foundational rule of his entire intellectual life. He insisted that the scientist must be an active, critical interrogator of nature, not a passive recipient of received wisdom. He believed that instruments and mathematics were the only reliable arbiters of truth, and that any claim, no matter how intuitively appealing or traditionally sacred, had to bow before the uncompromising authority of measured data. He demonstrated the awesome power of this approach with one of his most famous achievements, a breathtakingly accurate calculation of the Earth's radius. His method was a masterpiece of geometric ingenuity and meticulous fieldwork. He first located a high mountain near the town of Nandona in modern-day Pakistan. He carefully measured the mountain's height using a complex method involving trigonometric observations of the dip of the horizon. Then, from the summit, he used a large astrolabe to measure the angle between the horizon and the distant sea. This angle, known as the dip angle, is the key. He understood that his line of sight from the mountain peak to the horizon was tangent to the Earth's spherical surface, creating a right triangle with the Earth's center. Using the mountain's height as one side of the triangle and the dip angle, he could apply trigonometric formulas to solve for the Earth's radius. His result was a figure of 6,339.6 kilometers, a value that is within a mere 16.8 kilometers of the modern accepted average radius of 6,356.7 kilometers. The margin of error is less than 1/3 of 1%, an astonishing feat of precision for the 11th century, and a triumphant validation of his belief that the physical world could be understood and measured with mathematical certainty. This commitment to empirical verification extended to his groundbreaking work in comparative anthropology. When he traveled to the Indian subcontinent, he didn't just record the customs and beliefs of the people he encountered. He analyzed them with the same objective, critical eye he applied to astronomical data. He learned Sanskrit so he could study Hindu texts directly rather than relying on potentially biased translators. In his monumental work, Tia Letter 1 E2, 5 Qi Macron Q Malai El Hind, or A Verification of What is Said About India, he systematically described Indian society, philosophy, religion, and science. But he went far beyond simple description. He compared Hindu cosmological ideas with those of the Greeks and his own Islamic tradition, not to declare one superior, but to identify universal human tendencies in explaining the cosmos and to subject all of them to rational scrutiny. He criticized Hindu legends that contradicted observable geography, yet he also praised Indian advances in mathematics and medicine. He was, in essence, practicing a form of early ethnoscience, treating cultural beliefs as systems of thought to be understood on their own terms, yet still evaluated against the consistent standard of empirical reality. Al-Biruni's intellectual bravery is perhaps best illustrated by his stance on one of the most contentious cosmological debates of his era, the rotation of the Earth. While he ultimately concluded that the available evidence was insufficient to prove it definitively, he did not dismiss the idea out of hand, as most of his contemporaries did. He seriously entertained the heliocentric arguments of the ancient Indian astronomer Aryabhata and the Greek thinker Aristarchus. More importantly, he provided a devastatingly logical rebuttal to the primary objection against a rotating Earth: the argument that if the Earth spun, objects thrown vertically into the air would land far to the west. Al-Biruni correctly reasoned that this was a fallacy. He understood the principle of shared motion, intuitively grasping what we now call inertia. He argued that the atmosphere and everything in it would share the Earth's rotational motion. A stone thrown upward is already moving eastward with the Earth, and it retains that motion, so it would land directly back where it started. This was a stunning insight that cut to the heart of the problem, demonstrating that our sensory experience is not always a reliable guide to physical truth, and that only rigorous logical and experimental analysis can reveal the underlying mechanics of the cosmos. The legacy of Al-Biruni is the legacy of the scientific method itself, fully formed and operating at its highest level. He was the complete scientist, a master theoretician who could design elegant experiments, a precise observer who trusted his instruments over his intuitions, and a critical thinker who questioned every assumption. His work represents the culmination of a centuries-long evolution in thought, from the philosophical speculations of the Greeks to a disciplined, evidence-based practice of inquiry. He didn't just make individual discoveries, he codified the very process of discovery. In an age where authority so often trumped evidence, Al-Biruni stood as a towering figure of reason, proving that the path to true knowledge begins not with faith in the old, but with a courageous and systematic doubt, and ends only with the relentless, measurable, and mathematical verification of the real. But the story of how we came to understand motion is far more complex than a single apple falling on a single head. While Isaac Newton is rightly celebrated for his grand synthesis, the intellectual journey to his laws of motion was a slow, centuries-long dismantling of a deeply entrenched system, the physics of Aristotle. And some of the most crucial cracks in that ancient edifice were made not in 17th century England, but in the vibrant scholarly centers of the medieval Islamic world, by thinkers like Ibn Sina and Hibat Allah-Abul Barakat al-Baghdadi, who dared to question the fundamental principles of how objects move. To grasp the radical nature of their contributions, we must first fully inhabit the Aristotelian universe they were challenging. As we've discussed, Aristotle's physics was built on the idea that all motion is either natural or violent. Natural motion was an object's innate tendency to return to its natural place in the cosmos. Earth fell downward toward the center, fire rose upward. Violent motion, like an arrow flying through the air, was any movement contrary to this natural tendency, and it required a continuous external force to sustain it. This is why Aristotle believed an arrow kept flying, because the air displaced by its arrowhead rushed around behind it to constantly push it forward. The moment the propelling force stopped, the motion should, in his view, stop almost immediately. This framework was intuitively satisfying. It matched the everyday experience of a cart stopping when the horse ceases to pull. But it contained a fatal flaw, one that would puzzle natural philosophers for nearly 2,000 years. It couldn't adequately explain why a projectile continues to move after it has left the thrower's hand. This is precisely where Ibn Sina, known in the West as Avicenna, made his critical intervention. In the 11th century, he proposed a modification to Aristotelian physics that would become a cornerstone of medieval mechanics. He suggested that when a mover, like a human hand, sets an object in motion, it imparts to that object a certain quality, a force or a property that keeps it moving. He called this quality male kasri, often translated as violent inclination, or more famously, impetus. Think of it as a kind of kinetic energy loaned to the object by the initial mover. When you throw a stone, your arm doesn't just set it moving, it imbues the stone with a finite amount of this impetus. As the stone flies through the air, this impetus is gradually consumed, fighting against both the stone's natural tendency to fall and the resistance of the air. Once the impetus is fully spent, the stone's violent motion ceases, and it reverts to its natural motion, falling straight down. This was a profound departure. Ibn Sina was proposing that motion could be caused by an internal property of the moving body itself, not by the continuous external push of the surrounding medium. His theory elegantly explained why a projectile doesn't simply drop to the ground the moment it leaves your hand, and it began the crucial process of shifting the explanation for motion from the environment to the object in motion. A century later, an even more radical critique emerged from the mind of Hibat al-Abul Barakat al-Baghdadi, a philosopher and physician whose personal journey was as dramatic as his ideas. Originally a Jew who later converted to Islam, al-Baghdadi was known for his fiercely independent and critical intellect. He didn't just tinker with Aristotle's system, he challenged its very core assumptions about force and motion. His most brilliant insight came from a simple yet profound observation about falling objects. Aristotle claimed that the speed of a falling body is constant and proportional to its weight. A 100-pound weight would fall 100 times faster than a 1-pound weight. Al-Baghdadi, through careful observation and reason, realized this was wrong. He noted that when objects fall, they don't just move, they accelerate. Their velocity increases the longer they fall. This observation alone was a monumental breakthrough, but he took it a step further. He proposed that this increase in velocity, this acceleration, is directly related to the force acting upon the object. In his view, the weight of an object wasn't just a property defining its natural place. It was a constant force acting upon it, and this force is what causes the continuous increase in speed during a fall. This line of reasoning led him to a conclusion that sounds eerily familiar to anyone who has studied basic physics. Al-Baghdadi essentially argued that force is not the cause of velocity, as Aristotle believed, but the cause of change in velocity. He was drawing a fundamental distinction between uniform motion and accelerated motion, and he was linking acceleration directly to an applied force. This is a stunning prefiguration of Newton's second law of motion, which states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. While al-Baghdadi didn't formulate a precise mathematical equation, he had grasped the essential physical relationship. He understood that a constant force produces a constant acceleration, not a constant speed. This was a complete inversion of the Aristotelian framework and a giant leap toward the concept of inertia, the idea that an object in motion will stay in motion unless acted upon by a force. The intellectual courage required for these breakthroughs cannot be overstated. Ibn Sina and al-Baghdadi were not working in an intellectual vacuum. they were grappling with a philosophical system that had been perfected and revered for over a millennium. To suggest that Aristotle, the supreme authority on nature, had been fundamentally mistaken about something as basic as motion was an act of immense scholarly bravery. They were pioneers of a critical tradition that valued observation and logical consistency over blind adherence to authority. Their work created a vital bridge, a transmission of ideas that would eventually flow into Latin Europe. When thinkers in Oxford and Paris, like Jean Buridan and Nicole Orsmy in the 14th century, began developing their own theories of impetus, they were building directly upon the foundation laid by these Islamic scholars. Buridan's concept of impetus is virtually identical to Ibn Sina's, and it was this refined idea that helped later minds, including Galileo, begin to conceptualize a universe where motion could persist without a constant mover, ultimately clearing the path for Newton's grand unification. The laws of motion, therefore, are not solely a product of the scientific revolution. They are the culmination of a long, collaborative, and intercultural conversation that stretched from Athens to Baghdad and beyond, a conversation where medieval scholars provided the crucial missing links in our understanding of the physical world. While the medieval Islamic world was making crucial strides in understanding the physics of motion, an entirely different yet equally profound understanding of internal motion was being perfected thousands of miles away, one that saw the human body as a landscape of flowing rivers. In ancient China, a medical tradition was developing that would produce one of the most sophisticated and enduring models of physiology in the ancient world, centering on a concept that feels both familiar and wonderfully foreign: the continuous circulation of blood and energy. This system was codified in the foundational text of traditional Chinese medicine, the Huangdi Nijing, or the Yellow Emperor's Classic of Internal Medicine, a compilation of dialogues that likely reached its final form around the 1st century before the Common Era. Within its pages, we find a description of a closed-loop circulatory system where the heart acts as the central pump, propelling blood through a vast network of vessels in a continuous circuit. A stunningly accurate physiological insight that predates William Harvey's celebrated discovery in the West by over 1,600 years. To truly appreciate this achievement, we have to step into the conceptual universe of the Nijing. The ancient Chinese physicians did not dissect cadavers in the manner of the Greeks. Their understanding came from meticulous observation of the living body, from feeling the pulse at multiple points, and from a deep philosophical conviction that the human body was a microcosm of the natural world, governed by the same cycles and flows. Their model of circulation was not just about blood as a solitary fluid. It was an integrated system where a vital substance called Zhu, which we translate as blood, flowed in intimate concert with a life force called Qi, often described as vital energy. Think of it as a two-lane highway running through the body. Blood, or Zhu, was the material, nourishing substance, the yin aspect that carried essence to every part of the body. Qi, its energetic counterpart, the yang aspect, was the motive force that gave the blood its movement and direction. You cannot have one without the other. The blood provides a vessel for the Qi to ride upon, and the Qi gives the blood the power to move. This inseparable pair was understood to travel together through an intricate network of channels known as the Jing Luo, or the meridian system, creating a complete, closed circuit of life-sustaining flow. At the very center of this dynamic system sat the heart, which the Nijing explicitly identifies as the sovereign or ruler of the body. The text states, "The heart governs the blood and the vessels," and it describes the heart's function as that of a powerful pump, responsible for the continuous and rhythmic movement of this blood-Qi mixture throughout the entire body. This was a physiological, not a philosophical, role. The heart's pumping action was what created the pulse, and the skilled physician could read the state of the entire internal system by carefully feeling the pulse at various points along the wrist, each point believed to correspond to a different major organ system. This wasn't just checking for a heartbeat, it was a complex diagnostic art, assessing the strength, rhythm, and quality of the circulation to determine the balance and health of the internal organs. By recognizing the heart as the central engine of this circulatory network, the ancient Chinese physicians arrived at a fundamental truth of human biology, completely independent of the Western anatomical tradition. Where their model diverges most strikingly from the modern one is in its purpose and pathways. While William Harvey in 1628 described a system of arteries and veins with a one-way flow driven by the heart, the Chinese system was more holistic and functional. Their vessels, or mai, were conduits for the dual flow of blood and qi, and their health was defined by unimpeded, smooth circulation. The concept of a blockage was central to their understanding of disease. If the flow of qi and blood became stagnant or obstructed in a particular channel, it would lead to pain, dysfunction, or illness in the area served by that channel. The therapeutic goal, therefore, was to restore the smooth flow. This is the entire rationale behind techniques like acupuncture. The insertion of fine needles at specific points along the meridians was not aimed at injecting a substance, but at removing obstructions, unblocking the vessels, and reharmonizing the circulation of qi and blood, much like clearing a debris-choked river to restore its natural current. Moxibustion, the burning of mugwort near the skin, served a similar purpose, using warmth to stimulate and move the stagnant flow. The sheer prescience of this ancient circulatory theory is breathtaking when you place it in its historical context. For over a millennium in the West, the dominant model was that of the Roman physician Galen, who believed that blood was produced in the liver from food, consumed as fuel by the organs, and that it ebbed and flowed in the vessels like tides in the sea, with two distinct types of blood in the veins and arteries. The Chinese model of a continuous cyclical flow driven by a central pump was a far more accurate and dynamic concept. It presented the body not as a static collection of parts, but as an active, flowing process. Health was not a state of being, but a state of doing, a state of unimpeded circulation. The tragic disconnect, of course, is that these two brilliant insights, one from the East and one from the West, developed in complete isolation from one another. The Neijing's profound understanding remained confined to its own cultural sphere, leaving European physicians to slowly and painstakingly rediscover the principle of circulation centuries later. Yet, the legacy of this ancient theory endures not as a historical curiosity, but as the living foundation of a medical practice that continues to heal millions, a testament to the power of observing the living body in its entirety and perceiving the vital, pulsing river that sustains us all. Yet while ancient thinkers were mapping the circulation of blood and the flow of qi, a Chinese inventor and astronomer was turning his attention to a far more violent and unpredictable force of nature. In the year 132 of the Common Era, during the Han Dynasty, a brilliant polymath named Zhang Heng unveiled a device so ingenious and beautiful that it must have seemed like something from a myth. He presented the court with what he called an instrument for measuring the seasonal winds and the movements of the earth, but we know it today as the world's first seismoscope. At a time when earthquakes were universally seen as expressions of divine displeasure or the stirrings of mythical creatures, Zhang Heng's invention proposed a radical alternative, that these terrifying events were physical phenomena that could be measured, quantified, and their source located from a great distance. Imagine a magnificent bronze urn, perhaps 6 feet in diameter, ornate and ceremonial in its appearance. Adorning its surface were 8 dragons, equally spaced, each one poised with its head facing downward. Curled within each dragon's jaws rested a delicate bronze ball. Directly below each dragon, with mouths wide open, sat 8 corresponding bronze toads. The symbolism was rich and unmistakable to the Han court. The dragons represented power and the heavens, while the toads, associated with water and the moon, represented the earth. This was not just a machine, it was a work of art that embodied a cosmic philosophy. The real magic, however, was hidden from view inside the sealed vessel. While the exact mechanism remains one of history's great tantalizing mysteries, the most compelling theory proposed by modern scholars suggests an apparatus of stunning simplicity and intelligence. It is believed that a heavy, inverted pendulum was suspended freely in the center of the urn. Arranged around this pendulum, likely connected by a system of levers or linkages, were 8 arms, each one pointing toward a dragon on the vessel's exterior. The brilliance of the device was in its operation. When an earthquake's seismic waves, the vibrations that traveled through the ground reached the seismoscope from a specific direction, they would cause the entire urn to shudder. The heavy internal pendulum, however, thanks to the principle of inertia, would tend to stay still. This relative motion between the moving urn and the stationary pendulum would cause the pendulum to swing or knock against the internal lever arm facing the direction of the earthquake's epicenter. This action would, in turn, trigger a mechanism that released the bronze ball from the corresponding dragon's mouth. The ball would then clatter down directly into the waiting mouth of the toad below with a loud, resonant clang. The specific dragon that released its ball did not just signal that an earthquake had happened. It pointed like a compass needle in the direction from which the tremors had originated. It was a device of astonishing prescience, transforming an invisible, terrifying force into a clear, directional signal. We know the device worked because the historical records tell a famous story. On one occasion, a dragon released its ball, though no one in the capital had felt the slightest tremor. Skeptics dismissed it as a mechanical failure until several days later, a messenger arrived from a province hundreds of miles away in the direction the dragon had indicated, reporting a major earthquake that had devastated the region. This single event proved the seismoscope's incredible sensitivity. It could detect quakes far beyond the range of human perception, acting as a remote early warning system. Zhang Heng had effectively invented the concept of instrumental seismology. He demonstrated that you did not need to be at the center of the chaos to study it. You could use a carefully calibrated instrument to gather objective data about an event happening a vast distance away. This shift from subjective human feeling to objective mechanical measurement is a cornerstone of all modern science. The true legacy of Zhang Heng's seismoscope lies not in the debated specifics of its pendulum and lever design, but in the profound scientific principle it embodied. It was a physical declaration that the natural world, even in its most chaotic and destructive moments, operates according to consistent physical laws that can be understood and measured. By creating an instrument to capture and quantify an earthquake, he was rejecting the supernatural explanations of his era and championing a worldview based on cause and effect. He was searching for a pattern in the chaos, a signal in the noise. This fundamental impulse to build tools that extend our senses and translate the invisible forces of nature into readable data is the very engine of scientific progress. Every modern seismograph that traces jagged lines on a rolling drum, every satellite that measures minuscule shifts in the Earth's crust, is a direct descendant of that magnificent bronze urn with its 8 silent dragons waiting for the Earth to speak. Now let's travel to ancient China, to a world of oracles and emperors, and consider a text that began as a manual for divination, but would one day reveal itself to hold a key to the digital age. The I Ching, or the Book of Changes, is one of the oldest Chinese classics, a work that for millennia has been consulted for wisdom, for guidance on statecraft, and for glimpsing the patterns of the future. At its heart is a simple but profound duality, the solid, unbroken line representing Yang, the active, creative, and light principle, and the broken line representing Yin, the receptive, yielding, and dark principle. These two fundamental symbols are combined into 8 trigrams, which are then paired to form 64 hexagrams, a complete system intended to model every possible situation in heaven and on earth. Yet, beneath this layer of philosophical and mystical interpretation lies a startlingly rigid and mathematical skeleton. The act of consulting the I Ching, traditionally through the casting of yarrow stalks or coins, is essentially a process of generating a random six-line figure, a hexagram. Each line is either solid or broken, a binary choice. The entire system, therefore, is a combinatorial structure built from a sequence of 6 positions, each of which can be in one of 2 states. Unknowingly, the sages who developed the I Ching had created the world's first documented binary code. This ancient system of binary patterns remained a fascinating philosophical curiosity in the West until the late 17th century, when it landed on the desk of the German polymath Gottfried Wilhelm Leibniz. Leibniz was a man obsessed with a magnificent dream. He wanted to create a characteristica universalis, a universal formal language that could reduce all human thought and logical reasoning to calculation. He believed that if all complex concepts could be broken down into simple, fundamental ideas, and if those ideas could be represented by unique symbols, then disputes in philosophy and theology could be settled not with passionate arguments, but with the dispassionate and certain logic of mathematics, with the triumphant declaration, "Let us calculate." It was in pursuit of this grand vision that he was laboring on the problem of representing numbers in the most pure and efficient way possible. He was tinkering with base systems beyond our familiar base 10, and he found himself drawn to the simplest base of all, base 2, the binary system. Leibniz's breakthrough was the realization that any number could be represented using only 2 digits, 0 and 1. In his system, the positional value doubles with each place, just as it increases by a factor of 10 in the decimal system. So the rightmost digit represents ones, the next represents twos, then fours, then eights, and so on. A 1 in a given position means you include that power of 2. A 0 means you exclude it. The number 5, for instance, is written as 1 0, 1 in binary, 1 4, 0 2s, and 1 1. This was a theoretical marvel, but to Leibniz it was more than just arithmetic, it was theology. He saw profound metaphysical significance in this system. He wrote that the binary system, with its genesis from nothing 0 and the unity 1, mirrored the Christian doctrine of creation ex nihilo, where God, the One, creates the entire universe out of nothingness. For him, the fact that all numbers could be generated from this primal duality was a powerful symbol of divine harmony and order. Then, in the year 1679, a fateful correspondence arrived. A French Jesuit missionary named Joachim Bouvet, who was stationed in China and deeply immersed in its culture, sent Leibniz a letter. Enclosed were diagrams of the 64 hexagrams of the I Ching, arranged in a circular sequence often attributed to the philosopher Shaoyong. Leibniz was electrified. Here, from the other side of the world, was a visual representation of his own binary system. He immediately recognized that the solid yang lines could be read as ones and the broken yin lines as zeros. The sequence of hexagrams, when read from the bottom up, perfectly illustrated a binary count from 0 to 63. The hexagram for Earth, 6 broken lines, was binary 000000. The hexagram for Heaven, 6 solid lines, was binary 111111 or 63. Leibniz saw this not as a coincidence, but as a miraculous validation of his belief in a universal rationality, a fundamental mathematical truth that had been discovered independently by 2 vastly different civilizations. For him, the I Ching was not a book of magic, but a primordial form of his own universal calculus, a philosophical proof that the architecture of reality was, at its core, binary. The legacy of this connection is nothing short of world-changing. While Leibniz saw the binary system primarily as a philosophical and theological marvel, and the I Ching's practitioners used it for divination, their convergence planted a seed. That seed would lie dormant for centuries until the advent of electrical engineering. The great inventors of the computing age, figures like Claude Shannon, realized that this abstract binary logic was the perfect model for building electronic circuits. A switch can be either on or off. A circuit can carry a high voltage or a low voltage. A magnetic domain can be polarized in one direction or another. This simple two-state physical reality is the perfect embodiment of the binary 1 and 0. The entire digital universe we now inhabit, every smartphone, every internet search, every piece of software that defines modern life is built upon this foundation. Every video stream, every text document, every complex artificial intelligence is, at the most fundamental level, an unimaginably long string of binary digits, a cosmic tapestry of ones and zeros woven together. The I Ching did not invent the computer, but it provided a stunningly early and sophisticated philosophical blueprint for a universe understood through binary opposition and combination. It stands as a powerful testament to the human intuition that the complex beauty of the world, and perhaps even the flow of fate itself, might ultimately be reducible to a sequence of simple yes or no questions written in the most ancient of codes. As we move from the intricate binary patterns of the I Ching, we find another ancient thinker whose gaze was fixed not on abstract codes, but on the vibrant, living tapestry of the earth itself. Stepping into the sun-drenched gardens of the Lyceum in Athens, we encounter Theophrastus of Erissos, the appointed successor to the great Aristotle. While his mentor had attempted to systematize all of knowledge, from the motions of the heavens to the logic of argument, Theophrastus made a deliberate and profound choice. He turned his formidable intellect to the ground beneath his feet, to the forests, and to the cultivated fields, dedicating his life to the patient study of the plant kingdom. In doing so, he earned a title that echoes through the centuries, the father of botany, and in his work we can see the clear, early roots of ecology and environmental science. Unlike the grand cosmological theories of his predecessors, Theophrastus's genius was in the power of meticulous, systematic observation. His two surviving botanical masterpieces, Inquiry into Plants and On the Causes of Plants, are not mere lists of herbs. They are comprehensive scientific treatises that display a methodology startlingly modern in its approach. He didn't simply name plants, he dissected them. He categorized hundreds of species based on their physical structure, their morphology, paying close attention to the differences between roots, stems, leaves, flowers, and fruits. He distinguished between monocotyledons and dicotyledons, noting the fundamental difference between plants that sprout with a single seed leaf and those with two, a classification that remains foundational in botany today. He grouped plants into trees, shrubs, undershrubs, and herbs, creating a logical framework for understanding the plant world based on their observable growth patterns and life cycles. He was a true taxonomist, creating order from the overwhelming diversity of nature by focusing on comparative anatomy long before the term even existed. But Theophrastus was far more than a classifier. He was an ecological thinker. He understood that plants were not isolated entities but were deeply interconnected with their environment, a concept that is the very soul of modern ecology. He carefully documented how soil type, water availability, and exposure to sunlight could dramatically affect a plant's health, size, and even its fragrance. He noted how certain trees, like the fir, thrived on north-facing slopes where they received less direct sun, while others preferred the warmth of a southern exposure. He described the concept of plant succession, observing how a patch of disturbed ground would first be colonized by pioneer species like grasses and weeds, which would then be gradually replaced by shrubs and eventually trees, a process of natural community development that ecologists still study today. He even recorded the intricate relationships between species, detailing how the shadow cast by a tall walnut tree could inhibit the growth of plants beneath it, an early observation of allelopathy, where one organism produces biochemicals that influence the growth of others. His curiosity extended beyond the green world into the very substance of the earth. In his small but significant work on stones, Theophrastus turned his systematic mind to the mineral kingdom. He described and categorized various rocks, minerals, and gems, noting their properties: hardness, color, texture, and how they reacted to heat. He discussed the mining of metals like iron and the quarrying of marble, and he provided what is likely the first written account of the magnetic properties of lodestone. While not a geologist in the modern sense, his effort to logically classify the non-living world demonstrated the same drive to impose order on nature's complexity. Furthermore, in his writings on weather signs, he connected atmospheric phenomena to future environmental conditions, carefully recording how the behavior of animals, the appearance of the sky, and the direction of the wind could be used to predict storms and seasonal changes. This was practical, observational science aimed at understanding the forces that shaped the living world. The legacy of Theophrastus is the legacy of a shifted gaze. He redirected the course of natural philosophy from the cosmic and the theoretical to the local and the empirical. Where others looked up at the stars, he looked down at a single leaf, understanding that the universe's grand secrets were also encoded in the veins of a plant and the composition of the soil. His work established botany as a serious scientific discipline, independent from medicine or agriculture, worthy of study in its own right. His ideas, preserved and transmitted through the ages, directly influenced the great herbalists of the Renaissance and provided a foundational text for the scientific revolution in biology. When Carl Linnaeus developed his modern system of taxonomic nomenclature in the 18th century, he was building upon the structural framework that Theophrastus had laid down over 2,000 years earlier. More than that, his holistic view of plants in their environment, his understanding of their interactions and dependencies, makes him a true intellectual forefather of ecology. He taught us that to understand life, one must first learn to see the world not as a collection of isolated objects, but as a deeply interconnected and ever-changing web, a lesson that resonates with ever greater urgency in our own time. Yet, as we consider the clockwork cosmos envisioned by Democritus, a universe of atoms falling in perfect parallel lines through an infinite void, we are confronted with a profound philosophical problem. In such a strictly deterministic system, where every collision and every entanglement is the inevitable result of a prior chain of causes, where is the room for free will? How could new things ever come into being if the future was already locked into a preordained path by the past? It was to solve this very dilemma that Epicurus made one of his most ingenious and controversial modifications to the atomic theory, introducing a concept so subtle and slight that it was almost imperceptible, yet its implications for the cosmos were earth-shattering. He called this the clinamen, the atomic swerve. Imagine the infinite rain of atoms, all descending eternally downward in the void like an endless cosmic waterfall. According to Epicurean physics, this was their natural motion. But Epicurus proposed that at utterly random and uncaused moments, an individual atom would undergo a minute spontaneous deviation from its straight path. This swerve was not a large, dramatic turn. It was the smallest possible divergence, just enough to break the relentless chain of cause and effect. Think of it as a single drop of water in that vast waterfall veering off by a fraction of a degree. This tiny, unpredictable event was enough to cause a collision with a neighboring atom, which would then set off a cascade of new interactions, entanglements, and combinations. The clinamen was the seed of chaos in an otherwise orderly system, the mechanism that introduced spontaneity, novelty, and ultimately, the possibility of a world that was not predetermined. For Epicurus and his Roman interpreter Lucretius, this was not merely a physical hypothesis, it was an absolute necessity for human freedom. If our minds and souls are, as they believed, composed of particularly fine and swift atoms, then the clinamen provided a physical basis for free will. Our choices are not simply the predetermined results of prior atomic configurations. At the moment of decision, a swerve in the soul atoms could allow us to break from the causal chain and initiate a new action from within ourselves. This was a powerful rebuttal to the fatalistic philosophies of his time, offering a way to reconcile a materialistic universe with our deep-seated intuition that we are the authors of our own actions. The swerve meant that the future was not written, that our lives were not just following a script composed at the beginning of time, but were genuinely open to our own influence and choice. Now, while Epicurus introduced the clinomen as a philosophical device to solve a problem of free will, its eerie resonance with a cornerstone of modern physics is nothing short of astonishing. The strict determinism of classical physics, which reigned from Newton through Einstein, has been fundamentally challenged by the advent of quantum mechanics. In the quantum realm, the behavior of particles is not a matter of certain cause and effect, but of probability and inherent uncertainty. Events at the subatomic level, such as the exact moment a radioactive atom will decay or the path a photon will take, are fundamentally unpredictable. They are governed by chance, by a built-in randomness that is a feature of the universe, not a flaw in our knowledge. This quantum indeterminacy is the modern scientific counterpart to the Epicurean swerve. Both concepts introduce an element of spontaneity and unpredictability at the most fundamental level of reality, breaking the chain of strict determinism and allowing for genuine novelty to emerge in the cosmos. The parallels, however, must be understood within their distinct contexts. Epicurus's swerve was a macroscopic, philosophical idea designed to explain free will and cosmic diversity. He had no experimental evidence for it, and it was conceived to operate on atoms as whole entities. Quantum indeterminacy, on the other hand, is a microscopic mathematical reality born from a century of rigorous experimentation and is woven into the very fabric of fields and forces. Yet the conceptual bridge is undeniable. Both systems reject a universe that is a giant, predictable machine. Both acknowledge that for a complex, creative, and open-ended universe to exist, a universe with stars, planets, life, and conscious beings capable of making choices, there must be an element of chance woven into the foundational laws. The clinomen was a brilliant philosophical intuition that, against all odds, prefigured one of the most startling and counterintuitive discoveries of the 20th century, that the universe at its heart possesses a fundamental and irreducible element of randomness, a cosmic dice game that makes reality far more interesting and far less predictable than anyone could have ever imagined. But while Theophrastus was meticulously cataloguing the plant life of Greece and Lucretius was contemplating the unpredictable swerve of atoms, a scholar in the bustling intellectual capital of 9th century Baghdad was observing the living world with a revolutionary new lens. His name was Abu Uthman Amr ibn Bar al-Kinani al-Fukemi al-Basri, though he is known to history by the nickname al-Jahiz, which translates to the goggle-eyed. And in his monumental 7-volume Kitab al-Hayawan, or Book of Animals, he wove together zoology, anecdote, philosophy, and theology to produce a work containing an idea so prescient it seems to defy time itself. Within its pages, he described a dynamic, competitive natural world where animals struggle for resources, develop new characteristics to survive, and pass these advantageous traits on to their descendants. A stunningly clear articulation of the core principles of natural selection and adaptation, written a full millennium before Charles Darwin was even born. Al-Jahiz's starting point was a fundamental observation of nature's overwhelming fecundity. He noted that if all the descendants of a single pair of animals were to survive and reproduce, they would quickly overrun the entire Earth. Yet the world remains in a state of balance. Why? Al-Jahiz reasoned that this balance is maintained by a constant, inescapable struggle for existence. In his own words, he described how all creatures are engaged in a perpetual competition for the necessities of life: food, water, shelter, and the means to avoid being eaten. He saw this struggle as the invisible hand that shapes the living world, a universal principle connecting the smallest insect to the largest predator. He observed that mosquitoes must outmaneuver the slap of a human hand to feed, and that mice must constantly devise new strategies to evade the ever-watchful cat. This was not a peaceful, harmonious creation, but a dynamic arena of conflict and survival, where every advantage could mean the difference between life and death. From this foundational struggle, Al-Jahiz drew his next brilliant conclusion, the mechanism of adaptation. He proposed that in order to survive this relentless competition, animals acquire new characteristics and habits that help them secure food and avoid danger. His book is filled with vivid examples of what we would now call adaptive traits. He described how certain animals develop camouflage, their colors and patterns blending seamlessly with their environment to hide from predators. He noted how predators, in turn, evolve sharper claws, stronger limbs, and cunning hunting strategies to overcome the defenses of their prey. He even suggested that some creatures change their behavior based on their circumstances, a form of behavioral adaptation. This was a world in flux where the pressures of the environment actively mold the forms and behaviors of its inhabitants over time. He was moving beyond a static description of nature to a dynamic theory of how nature transforms itself. Perhaps his most profound insight, the one that truly anchors him as a precursor to evolutionary theory, was his concept of the inheritance of these acquired advantages. Al-Jahiz did not believe these survival traits were lost with each generation. He explicitly stated that these new characteristics, developed through the struggle for life, are then passed down from parents to their offspring. He wrote that an animal's descendants would inherit not just its physical form, but also the very skills and traits that allowed it to survive. In his view, a lineage of animals could, over successive generations, become progressively better suited to its particular niche in the world. This process of descent with modification is the very engine of evolution. While he lacked the specific mechanism of genetics, he had correctly identified the core feedback loop. Environmental pressure selects for advantageous traits, and those traits are heritable, leading to the gradual transformation of species over long periods. To truly appreciate the staggering originality of these ideas, you have to place them in their historical context. In the 9th century, the dominant explanations for the diversity of life were either the static creationism of the Abrahamic traditions, where God created all species in their current, perfect forms, or the classical ideas of Aristotle, who also saw species as fixed and unchanging types. Al-Jahiz's vision was a radical departure from this fixity. He was proposing a world of constant, dynamic change, driven by natural, observable forces rather than a single divine act. He was replacing a snapshot of creation with a moving picture of continual adaptation. His framework saw nature not as a completed masterpiece, but as an ongoing creative process. So why did this brilliant, comprehensive theory not immediately spark a biological revolution? The reasons are complex. Al-Jahiz's Book of Animals was an encyclopedic work that mixed sharp scientific observation with folklore, poetry, and theological digressions. His revolutionary ideas were not presented as a single, standalone thesis, but were woven throughout a much larger and more eclectic tapestry. Furthermore, the intellectual transmission of his work to medieval Europe was fragmented. While his books were influential in the Islamic world, their full impact on the Latin West was limited. The conceptual leap he made was so immense that it likely required a broader scientific infrastructure, better taxonomy, deeper paleontology, and a more widespread acceptance of deep time to be fully validated. His insights were a seed that fell on fertile ground, but one that needed a much longer winter to germinate. The legacy of Al-Jahiz is not that he discovered evolution before Darwin, but that he demonstrated the remarkable power of the human mind to discern profound natural truths through pure observation and logical deduction, even without the vast evidence of the fossil record or the concept of geological time. He looked at the same world everyone else saw, the struggle, the camouflage, the inheritance of traits, and he connected the dots into a coherent and powerful theory. His work stands as a monumental achievement in the history of science, a testament to a mind that dared to see the living world as a process of becoming, not just a state of being. He provided a crucial link in the long chain of biological thought, a voice from the 9th century whispering the principles of natural selection, waiting for the world to be ready to hear them on a global scale. And so we arrive at the final theory on our journey, one that brings us full circle, back to the very beginning of this exploration of human curiosity and back to the Greek world that gave us so many of these foundational ideas. After contemplating the infinitesimal world of atoms and the vast revolutions of the heavens, we conclude with a concept that sought to unite them all into a single, breathtaking vision of cosmic harmony, the Pythagorean music of the spheres. This was not a theory about what the universe is made of, but about how it sounds, an audacious claim that the cosmos itself is a sublime, ongoing musical performance, a symphony written in the language of mathematics. The Pythagoreans, as we've seen, were possessed by a singular, powerful conviction that number and mathematical ratio were the ultimate reality behind the world of appearances. This belief was cemented by their discovery of musical harmonics, where they found that the most pleasing consonant intervals, the octave, the fifth, the fourth, were produced by strings whose lengths were in simple, whole number ratios. To them, this was not a coincidence, it was a profound revelation. If the abstract beauty of mathematics could so perfectly govern the sensory beauty of music, then surely the entire universe, the grandest creation of all, must be structured according to similar harmonic principles. They imagined the planets, the wandering stars, each fixed to its own crystalline sphere, rotating around the central fire of the universe. As these immense spheres turned, they reasoned, they must necessarily produce a sound, a hum based on their orbital speed and distance. Just as the different lengths of a lyre's strings produce different notes, the varying dimensions of the planetary orbits would each generate their own distinct pitch. This is where the theory blossoms into its full poetic splendor. The Pythagoreans proposed that these individual planetary notes, determined by celestial mathematics, would blend together into a continuous, magnificent chord, a harmony of the spheres. It would be the most beautiful music imaginable, the sound of cosmic order itself. So why, then, can't we hear it? Their answer was as ingenious as the theory itself. They argued that this celestial symphony has been the constant background noise of our existence since the moment we were born. We are so perpetually immersed in it, so accustomed to its presence, that we have become deaf to it. In the same way, a blacksmith eventually becomes deaf to the constant clang of his own hammer. It is the ever-present sound of reality, and our senses, tuned to detect change and difference, simply filter it out. This was a truly stunning synthesis, linking the physics of the heavens directly to the mathematics of aesthetics, creating a universe that was not just orderly, but beautiful, and whose beauty was of a kind that could be understood by the human mind. While this specific vision of a singing cosmos is not scientifically accurate, its philosophical impact was so immense that it resonated for millennia, acting as a powerful inspiration for one of the key architects of modern astronomy, Johannes Kepler. Living in the early 17th century, Kepler was a man caught between two worlds. He was a brilliant mathematician and a meticulous empiricist, working with the precise observational data of Tycho Brahe. Yet he was also a deeply mystical thinker, still steeped in a Neoplatonic and Pythagorean worldview. He could not accept that the planets moved without a deeper, more beautiful reason than mere physical laws. He was utterly convinced that God had constructed the solar system according to a perfect geometric and harmonic plan, and he dedicated a significant part of his life to discovering the score to this divine symphony. His first great work of cosmic harmony was his Mysterium Cosmographicum, in which he proposed that the relative distances of the 6 known planets from the Sun could be explained by nesting the 5 Platonic solids within one another. It was a geometric model of the solar system, a tangible, three-dimensional expression of divine order. But he didn't stop there. Decades later, after he had formulated his three laws of planetary motion, he published his monumental work, Harmonices Mundi, or The Harmony of the World. In this book, he attempted to find the actual music of the spheres. He took the astronomical data he had painstakingly derived, the planets' orbital speeds at their closest and farthest points from the Sun, their perihelion and aphelion, and he treated these velocities as if they were musical pitches. He assigned each planet a range of notes based on its changing speed along its elliptical path. Mercury, with its wildly varying velocity, had the greatest range, a full octave, while the slower, more stately Saturn could only manage a minor third. He then combined these planetary notes into intricate polyphonic phrases, literally composing little snippets of celestial music for the solar system. It was during this obsessive search for harmonic patterns in the orbital data that Kepler stumbled upon what would become his third law of planetary motion, the precise mathematical relationship between a planet's orbital period and its average distance from the Sun. The square of the orbital period is proportional to the cube of the semi-major axis. This was not a musical law, but a physical one, a cornerstone of modern astrophysics. And yet, he discovered it because he was looking for a musical ratio. The profound truth here is that Kepler's mystical belief in a harmonious cosmos, a belief inherited directly from Pythagoras, was the very motivation that drove him to sift through the numbers until he found a real, tangible, and elegant mathematical law governing the heavens. The music of the spheres was scientifically wrong, but it was philosophically and motivationally profound. It was a guiding star, a beautiful error that led to a beautiful truth. The true, enduring legacy of the harmony of the spheres, therefore, is not in the literal sound of planets, but in the powerful and persistent intuition it represents, the conviction that the universe is fundamentally comprehensible because it is structured according to elegant mathematical laws. This Pythagorean and Platonic faith is the unspoken bedrock of the entire scientific enterprise. It is the reason why Galileo could declare that the grand book of the universe is written in the language of mathematics. It is the reason why physicists today search for a theory of everything using complex equations and symmetries, believing that at the heart of the chaotic, buzzing complexity of the cosmos lies a simple, beautiful, and harmonious order. The music of the spheres was the original, poetic expression of this faith. It taught us to listen for the hidden music in the motion of the worlds, and in doing so, it inspired us to learn the mathematical language in which that music is written. It is a theory that fails as literal description but triumphs as a metaphor for the deepest ambition of science, to hear and to understand the silent, magnificent symphony of existence. And so, our journey through the corridors of ancient thought comes to a close. We have ventured from the sun-baked agora of Democritus, who envisioned an uncuttable atom, to the bustling libraries of Alexandria and Baghdad, where minds like Eratosthenes and Al-Biruni measured the world and the cosmos with breathtaking precision. We have seen Hippocrates shift the cause of disease from divine punishment to natural imbalance, and we have marveled at Sushruta's sophisticated surgical tools and Zhang Heng's earthquake-detecting dragons. We followed the logical thread spun by Anaximander, who saw humanity's origin in the water, and Al-Jahiz, who described a fierce struggle for existence shaping the animal kingdom. This was not a tour of quaint superstitions or lucky guesses. Each of these 30 theories represents a profound victory of the human intellect, a triumph of keen observation, relentless logic, and the courageous application of reason to a mysterious world. The common thread weaving through all these disparate ideas, from the atomism of Epicurus to the mathematical harmonies of Pythagoras, is a powerful and unwavering conviction that the universe operates according to consistent, comprehensible principles that can be understood by the human mind. These thinkers looked at the chaos of a storm, the complexity of a living body, or the majestic march of the stars and refused to accept "the gods did it" as a final answer. They believed that by carefully observing patterns, by asking how and why, and by trusting in the power of their own reason, they could uncover the underlying order of reality. This was the great shift from mythos to logos, a foundational turn that established the very possibility of science. They were building the first maps of knowledge, and while some of their maps were flawed, their commitment to the process of map-making was their true, enduring gift to humanity. This legacy is not merely a historical artifact, it is the intellectual DNA of our modern world. The scientific revolution was not a sudden explosion of light in a dark age of ignorance. It was a reawakening, a renaissance that was possible precisely because these ancient theories had been preserved, debated, and sometimes even suppressed, creating a fertile ground for later minds to rediscover and validate them. When Newton stood on the shoulders of giants, those giants included Democritus and Strato of Lampsacus. When Darwin pieced together the puzzle of evolution, he was walking a path first glimpsed by Anaximander and Al-Jahiz. The courage of Anaxagoras, who was persecuted for calling the sun a physical rock, paved the way for Galileo's own battles with authority. The story of science is not one of isolated genius, but a continuous, collaborative, and often interrupted conversation stretching across millennia. So, what does this incredible journey tell us about ourselves? It reveals a species driven by an insatiable curiosity, a relentless need to make sense of our place in the cosmos. It shows that the tools for understanding the universe were with us all along. The ability to observe, to question, to reason, and to imagine possibilities beyond the limits of our immediate senses. These ancient visionaries did not have particle accelerators or space telescopes, but they had the most powerful instrument of all the human mind, armed with logic and fueled by wonder. Their achievements stand as a permanent testament to the power of an idea, proving that a single, well-reasoned thought can echo for centuries, waiting for the moment when evidence and technology finally catch up to its brilliance. This exploration belongs to all of us. It's a shared inheritance of curiosity and reason. Now, we'd love to hear which of these ancient theories resonates most powerfully with you. Was it the staggering accuracy of Eratosthenes measuring the globe with a stick and a shadow? The haunting prescience of the I Ching's binary code foreshadowing our digital age? Or perhaps the lonely, revolutionary voice of Aristarchus, placing the sun at the center of our system 2,000 years before Copernicus? Let us know in the comments below which of these 30 theories do you find the most genuinely mind-blowing. And if you've enjoyed this voyage into the history of ideas, be sure to subscribe and hit the notification bell. We have many more journeys planned, exploring the moments where human thought dared to leap into the unknown and forever changed our understanding